Good morning, Astronomy 1020. Welcome back to part 2 of lecture 2. Our goal today is to practice using the stellar coordinates that you learned on Tuesday. I had time on Tuesday to introduce the coordinates and define them for you. And we did a lab on the celestial spheres where we hunted down some of the most famous stars in the nighttime sky. But knowing that we will be tested on this subject and knowing that it's not easy to learn your first time around, for the first part of today's class, I have a sequence of exercises in mind that will train you guys to get really good at the two types of coordinates that we use to describe stars in the sky. So we'll do a lot of sort of hands-on practice stuff. Also, we're going to be prepping for our homework today. There's going to be several questions on stellar coordinates, and people tend to find that a little bit of a challenge the first time around. For those of you who've taken my 1010 course and have seen this once before, this actually might be a nice lecture for you guys because you may actually start to understand it. Sometimes the second time through, it actually makes a little more sense. So you'll have to, Andrew and Mateus have taken my solar system course. We'll see how that goes. The second part of today's lecture, we're going to transition to talk a little bit about planetary orbits. We're going to learn about a famous astronomer named Johannes Kepler. He's important because he was the first person who correctly described the elliptical orbits of planets. And as we're going to be studying the orbits of stars around galaxies and binary stars, that stuff's going to be really important in this class. So, so there's sort of two-part play here today. And what I'd like to do is get right into it. Now, let's start by showing you guys a picture. And I want to see what you guys can remember or what you can sort of fake your way through using your notes. So let me begin today by showing you a slide of what you'll remember is called your local sky. Let me just check the chat. Okay, cool. So I want to show you guys, I think it's slide 47-ish, 49 rather. Function F5, 49. Okay, guys, this is a picture of your local sky. What do you guys remember about this? Now, by the way, sometimes you see me draw on the slides. I think you guys can do that too. I'd ask you to use that awesome power tastefully. But if you want, you can even circle things and point out from time to time. I don't mind if you do that, if that's helpful when we're talking. So can you guys tell me about any of this stuff here? What's this point on the local sky called?
The zenith.
Good, the zenith. How about over here? What's this arrow pointing to?
That arrow, isn't that Polaris?
Oh, pardon?
Polaris?
Polaris, yep. There's another name for it too. What do we call this?
NCP, the North
yes.
Celestial Pole?
North Celestial Pole. Excellent. Was that Sabrina? Who was that?
Yeah, that was me.
Okay. Oh, there you are. I'm scrolling through all the. I can see like 4 faces at a time, so when I hear someone, I start scrolling around. Nicely done, Andrew and Sabrina. Polaris is there, but technically speaking, it's the North Celestial Pole. That's a point in our local sky. How about this line here?
Celestial equator.
The celestial equator. That's the projection of Earth's equator onto the sky. Okay, now so you guys are impressing me. You know your vocabulary. I like it. What if I asked you guys, this might be a toughie. Can you guys tell me which direction the stars, how do the stars move through this local sky at night? What are the stars doing from our location? Does anyone?
Are they like going east or something? I don't know.
Well, when you say going east, do you mean towards the east? Let's be clear about this, Sabrina.
Okay.
They are going in a direction. Which direction do they travel? What about the sun? What does the sun do?
Oh, the sun? Is it north and south?
Nope.
It rises in the east and sets in the west.
There you go. I figured someone had heard that before. So Nick, it's a good bet that the stars also rise in the east and set in the west. But here's my problem, Nick. I could imagine a lot of different paths from east to west. For instance, I could imagine starting east and going like that to get to the west. Or I could go up over the zenith to get to the west. Or I could
I-
go like, yeah.
I think I have the answer. Is that the circumpolar stars? They never really rise or set. They just circle
Well, so
in the sky.
I'm talking about something that's related to that. Circumpolar stars are moving on what astronomers call, let's see if I can write this out. They're called diurnal tracks. Here's a fancy vocab word for you. Diurnal is the daily motion through the sky. So a simpler word for diurnal tracks would just be star tracks, but that sounds kind of silly, right? So the tracks that stars make are lined up with circumpolar stars, but I'm not asking about the subset of circumpolar stars. I'm just asking in general, how the hell do the stars go from the east to the west? I wanted to see if anyone already could answer that question. And I think thinking about it is also helpful. Even realizing you don't know will be useful here. So does anyone know how a star would go from the east to the west?
The Earth's axis and it's spinning.
Okay, so that's a good hint. If the Earth is spinning on its axis, then the tracks should be parallel to what line?
Celestial equator.
Exactly. Nice. So the thing to do is to remember that it's the Earth spinning that causes stars to move. So the star tracks, so to speak, will be, let's see here, perpendicular to the celestial equator. And somewhere buried in here, I have a slide for that. Here's slide 81. The colored rings that you see represent the diurnal motions of stars during the night and even during the day, except you can't see the stars during the day. But the stars are constantly rotating through the sky on tracks like this. If you are a particular star, you are pinned to the sky, kind of like pin the tail on the donkey, at some location. And then once you're pinned to that location, as Earth spins, you will move on a track which is parallel to the celestial equator. So you will rotate around the sky like this. And yes, you will rise in the east and set in the west. Now, the truth is that these tracks are approximately the tracks that stars will make through the Rhode Island local sky. So since we have to start somewhere, I figured why not start with our beloved home state. We're located at a latitude. Do you guys remember what our latitude is? What's the latitude of Rhode Island? Hey guys, give me a second to turn the heat down because I'm starting to burn up here. Okay, latitude of Providence, Rhode Island. What do you got?
Is it 42 degrees north?
Exactly, Nick, 42 degrees north. So the purpose in reminding you about that is, Nick, if latitudes go, if they go from 0 at the equator to 90 degrees north at the North Pole, 45 degrees is like half of a right angle, right? So it's kind of cool to learn astronomy from the state of Rhode Island because we are approximately halfway up the globe. So our position on Earth is a pretty ordinary sort of, it's a sort of good generic place to start learning about the tracks of stars. The picture you see here shows stars rotating at approximately a 42 or a 45 degree angle. The path that stars make change as you go from the North Pole to the equator. And your book has a couple of lovely pictures. Let me sort of show you them so that you can start thinking about this. If you were standing on Earth's equator, unfortunately, one thing I really dislike about the book's diagrams is they put north on the left-hand side. So please be careful of that. That's, you know, this slideshow has never had the same power that the, hold on a sec, guys. I should have a slightly better set of pictures in here. It's now that I think about it, it's probably time. It's time to do a big overhaul of my slides at some point. But let me see if I have a better picture here. Okay. This is what star tracks look like on the equator, function F524. Notice that if you're standing on the equator, you're rotating around on the equator, and from your local sky, the tracks that stars make are completely perpendicular to the north-south line. Or perpendicular to your meridian. They rise in the east, they go directly up overhead, and then they set in the west. What about the North Pole? The North Pole is even weirder. If you're on the North Pole, you're basically at the top of the spinning Earth. So stars actually don't rise or set on the North Pole or the South Pole. Stars just kind of orbit the sky. I've always thought it would be cool, not that I like extreme cold, but it would be cool to watch a sky rotation from the North Pole and watch stars kind of orbit your head. That would be kind of neat. In any case, the equator and the North Pole are extreme latitudes. For your average ordinary latitude, like Rhode Island's, the tracks kind of go at an angle. We'll describe the angle in just a moment. Sorry here, sometimes my taskbar shows up and sometimes it doesn't. I never understand that. So this is where we're starting, slide 81. And we're going to talk about the tracks that stars make. Okay, now I want to throw in the coordinates there so that we can talk intelligently about the motions of these stars. What are the names of the two coordinate systems that we use to describe stars in our sky? Can you guys refresh your memories in your book there?
The declination and the right ascension.
Yeah, so that's called the equatorial system. Let's do some review notes. Okay, so let's lock on me. And let's remind ourselves that we have, sorry, this is not a good marker. We have two coordinates for stars, and I need to review both of them with you. The one that, was that Kim, or who was that? That was Amy or Kim? Wait a minute.
Mia.
Mia, sorry, Mia. I knew it was 3 letters. Okay.
Okay.
Mia, Mia, you were talking about the equatorial system. And she's reminded us that the two angles are called right ascension and declination. RA and dec. And what's the name of the other system?
The horizon system.
Yeah.
I'm
And
going
the
completely
angles-
backwards on you. I'm sorry.
Pardon?
I'm going completely backwards on you. I'm sorry.
That's okay. The order is irrelevant, really. And what are those two angles called?
The altitude and the, I'm going to pronounce this wrong, the azimuth.
Perfect. Sometimes we say alt-az. Those are the nicknames. For instance, some telescopes have an alt-az mount. They go sort of along the horizon and up from the horizon. Okay, one of the things that gets real messy your first time through is being able to flip back and forth between these two coordinates without messing them up. I've got some practice in mind for us to sort of work on that. So let's start here. You guys might have to look at the definitions. Let's see who can handle this. Let's talk about the equatorial system. Remember, that's right ascension and declination, and it's kind of like latitude and longitude for the sky. The red ring is the celestial equator. What is the declination of the celestial equator? Let's get rid of this stuff. Oops. Can someone tell me the declination of the celestial equator? Is that too tough for you guys?
Is it the dotted line?
Well, the red line, the red circle, the whole thing, the whole red circle is the celestial equator. And I want to know the declination of that ring. All right. Could
Can
someone?
it be 0?
That's right. Very good. It's 0 degrees, because what is our definition, Mateus, of declination? Could you just read it from your notes? So this is, oops. Let me go back to, How did I
It's the
choose?
degrees of a star, positive or negative from the celestial equator.
That's right. So if you're on the celestial equator, you are 0 degrees. How did I choose my line thickness? Okay, I'm being silly here. Let's clear all drawings. Okay, so this is 0 degrees, the celestial equator. What about the north celestial pole? What's the declination of the north celestial pole?
Is it also 0?
Nope. We measure declination positive or negative.
Is it 90 degrees?
That's right. If I go, that's how I choose my line thickness. Okay, I got to remember that. Let me use purple here. If I go from here up to the north celestial pole, that's 90 degrees of declination. Okay, with that in mind, could someone give me a reasonable guess as to what the declination of the blue ring would be? Just guess a number that sounds good. Here's a hint, not 7,632. What would be a guess for the declination of the blue ring?
Should I say like 35? Well,
Yeah, we say positive when it's above the celestial equator. But Sabrina, I would totally agree with positive 35. That's a very reasonable guess. If I were going to guess even better than that, Sabrina, I would argue that if this ring, the celestial equator, is 0, and if the north celestial pole is positive 90, I would say this is about a third of the way up. So personally, if I were guessing, I would have guessed positive 30. But positive 35 is close and it's very reasonable. Okay, Sabrina, since you're so good, what would you guess for the purple ring? What would be the declination of the purple ring?
60?
Positive 60. How about the orange ring?
Negative 30,
Good. The yellow ring?
then negative 60. Wait.
Excellent. And then the south celestial pole would be negative 90. That's good. Okay, now you guys you're impressing me. Let's try some practice problems with the equatorial system, then we'll get over to that one, okay? Here's a problem that I think is good. Find the right ascension and declination of the 4 key points that we learned about last week in Earth's orbit. They are the spring equinox. They are the summer solstice. They are the fall equinox. And they are the winter solstice. Now listen, at first, this question probably doesn't make sense when you first hear it, because for most of our lives, we're used to thinking of the spring equinox and the summer solstice as a day of the year, March 21st, June 21st, and so on. But remember, the spring equinox and the fall equinox are not just days of the year, they're also points on the sky. And you can see that from this important diagram here, slide 77. The spring equinox can also be thought of as the point where the celestial equator intersects the ecliptic. Okay, I'm going to be throwing a lot of words at you, and I need to know that you can understand them. Someone remind me what definition 2 of the ecliptic is. What's definition number 2 of the ecliptic? Use your notes.
Definition 2, you said?
Please.
It's path of the sun against the background of the stars.
That's right. So the purple ring here represents the path of the sun, and the red ring represents the celestial equator. The spring equinox is one of the points in which they meet. The summer solstice is this point. The fall equinox is that point. The winter solstice is there. And by the way, not only are they points on the celestial sphere, but if you think about it, that means, slide 78, that they're also points on the sky. For instance, the spring equinox is an empty point in space just below the constellation Pisces. And every day or every night, that point rises and sets just like any other star. You've never noticed the point called the spring equinox, Because there's nothing there. There's nothing there for you to see rising and setting. Well, okay, that's mostly true. Once per year, a special astronomical object will appear for one day at the spring equinox. Do you know what that object is? Mateus is laughing because he might know. Can you guys guess what the special astronomical object is that appears at the spring equinox for one day out of the year?
Is it like the North Star or something?
No, it is a star, but it's not the North Star. A star appears at the spring equinox once every year, just for one day only. Mateus, do you know?
Is it the sun?
Yeah, guys, it's the sun, right? Let me tell you, that's where the sun's going to be on March 21st. And let me show you where the sun's going to be on June 21st. It's going to be in the foot of Gemini. And in December 21st, the sun will be in Sagittarius. That's what those points mean. They're telling you where the sun is on particular days of the year. Okay, your goal is we'll look at the diagram together. And I should probably give a little more space here. I want the right ascension and declination of all of those points. So let's start with the spring equinox. Look at the globe, look at your definitions. Can someone give me either the right ascension or the declination of the spring equinox? Hold on, I'm trying to get the students collapsed again. All right, and there you go, you're on the side. And let's go back. Okay, someone give me either the right ascension or the declination of this point.
Well, I know the date for the spring equinox.
All right, it's March 21st, but that's not going to be helpful here. We need coordinates, right ascension and declination. If you're having trouble, you could read me the definitions of right ascension or declination, and we could go from
Is
there.
it 0?
Which one are you giving me, Mateus?
The vernal equinox.
No. There are two coordinates that I'm asking for. If I say, give me a latitude and
All right.
longitude, and you say 0, that doesn't make any sense.
Oh, I got this. So because it's spring equinox starts on March 21st, so it'd be 0 hours and 0 minutes.
Very good.
For the
That's the
right-
right ascension.
And then the declination would be 0 degrees.
Excellent. So, Mateus, it wasn't that you were wrong. Your answer actually turned out to be correct for both, but I needed you to recognize that I needed two numbers. Okay, that was my beef. Okay.
Would you mind explaining how we got that? Because I'm a
Yeah.
little confused.
Okay.
Yeah, I'm a little confused also.
That's fine. So let's do it. So what we need to do, Kiana, is we have to be able to remember the definitions of those things. I can understand your confusion. So why don't you, Kiana, could you read me the definition of right ascension from your notes? Last class, I would
Yes.
have defined it for you.
It says hours and minutes of a star measured eastward from the spring equinox.
Right. So what that means is you remember that eastward is counterclockwise in space.
Yes.
So to measure right ascension, we start at the spring equinox and then we wrap around the globe like so. It's actually kind of like longitude, but we travel along the celestial equator. Since it's the hours and minutes measured eastward of the spring equinox, if you are at the spring equinox, that's the starting point. So you
Okay.
start at 0 hours. And then, Kiana, as you go around, it goes from 0 to 24 hours. It sounds like time, but it's not time. It is a coordinate measured in hours. That takes a little bit getting used to. Did that help?
Yes, that did.
Okay, good. And I hope that helped the other person. You guys did right to tell me you were confused, because this is confusing at first. Usually I can explain it enough if you can tell me where you're getting lost. All right. So let's also talk about why it was 0 degrees declination. Kiana, now read me the definition of declination. Should be right next to the right ascension.
I think my notes are a little jumbled up.
You're
I
winking,
just highlighted it, so like I don't know why I can't find it now.
It goes like that sometimes.
Oh, I found it. Okay. It says degrees, positive or negative from celestial equator.
Exactly. So in this case, we're going in the other direction. We start at the celestial equator, and we can go from 0 at the celestial equator all the way up to positive 90. That's what Sabrina was doing with us a moment ago. We can start at the equator and go down to the south celestial pole, which is negative 90. Now, Andrew knew that it was 0 degrees declination, and perhaps Mateus did too, because it was on the celestial equator. What's
Okay.
goofy here,
Okay.
Kiana, is the Earth is tilted sideways, so that's throwing you off a bit. Okay.
Okay. I see it now.
Because I was looking at also the autumnal equinox, that dot as like that would have to be 90 degrees also because of that dotted line that's right there. So that's where I
Hold
was
on,
confused.
wait a minute. Slow your roll, Nick. We're gonna do those next spots yet. Let's start with this. So Nick and Kiana will have you each try one. Nick, why
Okay.
don't you try to muscle your way through the summer solstice? So why don't you think about this? Why don't you see if you can give me either the right ascension or the declination of the summer solstice?
So am I going based on like eyeball here? Because that does look like it's only just a little bit above the celestial equator.
Right, but you'll
So-
notice they've given you a hint as to what the angle is from here to here.
So that small space right there is 23.5 degrees.
Right, now which coordinate is that? What did you just give me? Right ascension or declination?
The degrees would be declination, wouldn't it?
Excellent. So you
think.
did that good. So let's write this down. So for the summer solstice, we'll get to the RA in a second, but the declination would be positive 23.5 degrees. Good. So that's your deck. Now give me the RA if you can. And here you might want to think about what this is like a turn around the clock is 24 hours. So how many?
So sorry, I interrupted you. I have for my notes, it's obviously the Earth spins 360 degrees over 24 hours at 15 degrees per hour.
Okay,
And
but
then-
don't even, here's a hint, Nick. Don't even think in degrees, just think in hours. If you go all the way around the globe, that's 24 hours.
Mhm,
If you go halfway around the globe, how many hours is that?
180.
No. Once again, you're thinking in
Right.
degrees. You need to be thinking in hours. It does take a little getting used to.
So
If a
12.
spinner, so 12. So here, I would argue that you've only gone a quarter around the globe. So what would your right ascension be?
So 12 is half. It has to be less than 12.
Yep, half of 12.
6.
Good, and that's our right ascension. 6 hours. Okay, so it's good to practice this because it's a little confusing. Kiana, I want to have you try the fall equinox now.
Okay.
So we need a right ascension and we need a declination for the fall equinox. Remember, the declination's in degrees, but the right ascension is in hours.
Okay, I hate to interrupt, but what are we looking at yesterday's notes to review this?
What I was yes, Sabrina. I defined the equatorial coordinate system. I defined right ascension and I defined declination in our last class's notes, right at the end of class. Do you have that?
Our equatorial system, yes. Okay,
You
I
see
was
those?
just a little bit lost. I don't want to.
No. That's cool. That's why we're doing this live so that we can talk to each other. This is cool. I like it. Do you see those definitions now, Sabrina?
All right, so latitude. Wait,
No, not
it's
latitude. Go. That's geographic coordinates. We're talking equatorial coordinates, right?
yeah.
Oh, I'm sorry. It did say latitude of the sky. That's right. All right. What do you have on your paper? Just read it out to me.
I said I have declinations or degrees of the stars, positive or negative from celestial equator.
Right?
And then I just want to make sure I have the right stuff here.
Yeah. And then what do you have for RA?
So our right ascension, I have AS for some reason. RA. I have this in here wrong. Hours in minutes of a star measured eastward from the spring equator.
Yeah, equinox. Watch
Oh.
that handwriting.
Okay.
Okay, so Sabrina, let's think about how Nick just used those two definitions to figure out
Okay.
what the coordinates of this point were. Okay, so let's just slow down and see what happened here. To give the declination, he used the definition, it's your degrees positive or negative from the celestial equator.
Mhm.
So he started at the celestial equator as close as he could get to the summer solstice. And then for a moment, he was scratching his brain thinking, wait a minute, how am I supposed to know how many degrees that is? And then I showed him a hint. I was like, look, they might have tipped you off there in the diagram. So he said,
Okay.
oh, okay, so it's positive 23.5 degrees above the celestial equator because it's kind of marked there. Do you see that angle?
Yeah.
This is an angle, all right?
Okay.
The right ascension is measured in hours. 0 hours, 6 hours, 12 hours, 18 hours, 24 is 0 again. That's how we do right ascension, okay?
Okay.
It's weird because it sounds like time, but it's not time. It's a position measured in hours. You have to kind of get used to that. It's a little awkward at first. Okay, so we'll have you try in a second, Sabrina, but Kiana, since you were also a little confused at first, Kiana, can you give me the RA and DEC of the fall equinox?
Okay, so would it also be 0 like
Wait, when you
the
say
spring?
yes, but which coordinate are you talking about?
For the deck?
Very good. So it's still
Okay.
on the, it's back on the celestial equator. So the declination is clearly 0 degrees. How about the right ascension? Let's look at the picture again. So the right ascension is how many hours from here to here?
12?
Good.
Okay.
Nicely done. All right, and Sabrina, we're going to have you muscle through the next one. So the fall equinox is 12 hours. And now we're going to try the winter solstice. Okay, Sabrina, let's see if we can do this.
All right.
Sabrina, you want to start with the declination or the right ascension? Maybe declination is a good way to start. What is the declination of this point? Remembering that declination is degrees positive or negative from the celestial equator.
Okay. It's on the celestial equator, so
No, it's the point is on the ecliptic, actually. Watch out for that. The celestial equator is up here. It's the red ring. So the point
Okay.
is not on the celestial equator. It's like this.
Okay. So is the deck is going to be 23.5 degrees?
Almost. Remember that we go positive or negative from the celestial equator.
Negative. So
Negative
negative
23.5. Good. All right. So that's the declination. Negative 23.5. How about the right ascension? Remember, the right ascension, Sabrina, is the number of hours wrapping around eastward. Starting at the spring equinox, how many hours is it from there to, that's the closest point along the celestial
18,
equator.
right? 1800 hours?
1800 hours. Very good. Okay,
Oh.
good. So that was a good exercise for you guys because it's really confusing at first, and the best way to start to learn it is to muscle your way through answering those questions.
Okay.
So
I
you
think
have
what's sorry, I think what's confusing is that since the celestial equator, the line on that globe is at an angle, and instead of it being flat, it's harder to see like what's positive degrees and what's negative degrees because you have to look at it at an angle when you're looking at it at the picture.
Believe it or not, Nick, I'm well aware of that. And although I didn't intend to find a picture that was tilted like that, it turns out that that's really good for us because what makes this very confusing is hello, Julia, when we're answering these questions for our local sky, oftentimes it's tilted on the sky. So we have to be able to manage that tilt, okay?
Mhm.
We got to be able to manage that tilt. Okay, now so that was a little bit of practice with the equatorial system. Nick, trust me, we're going to get some more practice in our homework today, okay? Let's now practice with the horizon system, and we're going to play a little game together, a drawing game that I've invented called the Alpha, Beta, Delta, Gamma game. I can see, Julie, I can see you're at work at the, I don't know if that's a hospital or a medical center, but I think
I
that's
work in a
great.
physical therapy office.
Oh, okay, right on. So are we sneaking past the boss here? Do they not know we're in class?
Yeah, I'm just trying to do this really quick.
All right, we'll be real quiet.
So,
Okay. All right,
so I had
let's,
sent you an email.
I
think
did
it
see
was
the
Monday
email.
or
What was it
Tuesday.
about again, Julia?
So when I do the labs or the homeworks, I refer to last semester's lab because when you post it on Thursday, it's too late for me to do the work.
I really apologize for that, but last Thursday, what happens is it takes so long for the video to render. And Julia, sometimes I
so
get hungry and
long.
I go get a burrito and then I come back and I'm like, oh crap, I got to put it up. So, okay, so you're doing last semester so you can get going. And
so I just wanted to make sure that was okay. I want to make sure that the homework and the labs are the same this semester as last semester.
I'm going through great pains to make sure they are. Hopefully,
Okay.
there was one homework assignment that I did last semester where I kind of threw in a different one, and I haven't gotten to that point yet. But so far, they should be absolutely identical. But if you're still on when we get to the homework section, we can check your work. And I think it's Julia. I'm almost 100%.
I already have it submitted. It's submitted already on Blackboard. I just wanted to make sure.
One thing that you want to. Okay, yeah, no. As long as you're watching the whole thing and copying everything that we get down, you should be absolutely fine. All right.
Okay, perfect.
You
Thank
got
you.
it, Julia. And let's try to play this game together, okay? We're going to do a little drawing exercise that I think is going to help. If you have a ruler, this would be a good time to bust it out. Okay, we're going to make a two-dimensional view of our local sky. This is a good practice because you can use this to solve problems in the test by making a diagram. And this is going to be very similar to the three-dimensional picture that we made last time. So if you have a ruler on the centimeter side, go about halfway down your page and make a line about 10 centimeters long.
We need a whole page for this?
A good fraction of it, yeah. I think so anyways. I need a whole board for it, so probably. Okay, make your line 10 centimeters long and then put a dot at the middle at 5 centimeters. Okay. Now we're going to want to make a dome. So I know the radius of my dome is 5 centimeters. So go ahead and go about 5 from the center point, go about 5 centimeters up and put a dot there. And a trick that I use is I make a dot at 5 centimeters at a whole bunch of different locations. Basically, I'm just marking out the radius of my dome. One of the reasons I go through the trouble is I know that a neatly drawn diagram will really help my mind see the problem. If you make a shitty diagram, if you make a sloppy diagram, you're going to have a sloppy understanding of the material. Diagrams matter. Okay. I left before you because you didn't see me. That's how you. I saw you when I got on this. How about that? Not too shabby, right? You guys should have something like that on the page. We're making this two-dimensional. Which direction should we put north, class? We have to think about that stuff. Where's north going to be?
The right side?
Yeah, I always like to do it that way. This will be south. And even though this is two-dimensional, I'm just going to kind of shade in the ground. And I'm going to put an observer dude at the center of the field. Let us now draw in the observer's zenith. The zenith, as you guys reminded me earlier, is the point overhead. I labeled the zenith with a Z. Let's also draw in the north celestial pole. We'll make a line that goes from the observer's foot up to the northern sky. Let's label this NCP. And let's remind ourselves that on the sky there, that's where Polaris is. Let's also draw in our celestial equator, what Sabrina referred to as CE. The celestial equator can't really be drawn on this diagram because this is a north to south cross section of the sky. And the celestial equator is sort of an east to west circle. But we can at least draw where the celestial equator intersects. It should be at a 90-degree angle where it intersects the meridian. So I'll make a 90-degree angle. I'll put a dot there, and then I'm just going to kind of make a dashed line. And at this dot, I'm going to write CE for celestial equator. So go ahead and make your diagram look like my diagram. I'd like to draw attention to the fact that I can see 1, 2, 3, 4 angles on my local sky. I'm going to label those angles with the first 4 letters of the Greek alphabet. This is alpha. Alpha looks like a little Jesus fish. This is beta. Beta looks like a squiggly bee. Can you guys see that? That's a little light.
I can kind of see it.
Okay.
Last semester.
Yes, this is a classic, Andrew. I do this for both of my classes because it's such a useful exercise. Actually, Andrew and Mateus, you're going to start seeing some connections and you're going to start recognizing some things. But you guys should actually pipe down because you've had a little training before. It's important for these guys to stumble their way through this the first time and get confused, okay? I don't want the answers to come too quickly. Let's label the third angle gamma. Gamma looks like a squiggly Y. And then the fourth angle is delta, which looks like a squiggly D or a music note. I'm going to turn the lights up just a little bit. Okay.
So can I ask just one question before you continue? So basically you're just breaking up the local sky into just 4 quarters, basically.
I don't want to call them quarters because depending on where you are, they're not going to be even breakups. And you can see that I tried to make, I didn't put the North Celestial Pole exactly halfway up. So the only reason I would say don't call them quarters, Nick, is because they're not going to be 45, 45, 45. You know what I mean?
Okay.
Okay. All right, so here's my first question. One of these angles, alpha, beta, gamma, or delta, is a direct representation of your latitude on Earth. Why don't you look up your definition of latitude from last class notes, and I want you to think about it while I refresh my iced tea. One of those angles represents your latitude on Earth.
Degrees measured north.
Sorry, guys, there's a little bit of dehydration going around this apartment today, and my brain definitely needs it needs some water for me to get through this here. So do you guys know which angle represents your latitude? Take a guess.
Is it the one at the bottom?
Wait, which is the one at the bottom?
Is it
I'm
delta?
sorry, not the one with the Z is, I'm assuming.
Wait, hold on. Let me give you the names of them again, Sabrina. Alpha, beta, gamma, delta. Now, someone else had an idea. I heard someone shout or not shout, but say something.
Delta?
Okay, who said delta?
Brian?
Brian? Oh, where are you, Brian? I don't see you, but I hear you. Brian.
Yeah, I'm kind of being told today.
Oh, you're a troll today? That's okay. Brian, it's not that you're wrong. It's just that you're not right. Okay, so I want you to put your answer on pause for a minute. That's not the angle I was thinking of. For instance, Brian, do you have the definition of latitude handy in your notes?
I believe I do.
Why don't you read that out loud so we can think about it?
Degrees north of or south of the equator.
Right,
North pole 90 degrees.
right. So if latitude is your degrees north or south of the equator, how should that translate onto the sky? I think I
It
know how
should
to
be-
help. Oh, yeah?
It should be like, if it's 90 degrees, it's just going to point straight up to the zenith.
No. The latitude is only 90 degrees if you're on the North Pole. So that was a sample, an example of how to use latitude. I don't want you getting distracted by the 90 degrees. I think I better help with a little drawing here. Underneath, let's draw the Earth, okay? Give a little space. Let's draw a circle representing the Earth. Thank you, Frisbee. Let's imagine we have a dude standing here. Let's draw in the North Pole of Earth. Like so. That's the North Pole.
Canada, you're 2 months.
That's the
Northman,
South Pole.
Either it could be a limb.
And let's draw in the equator.
6 months now. We got the 6 monther. Another one. So it means that you're 5 months, or you're 5 gifted. Then love, you're 2 months. Stranger, you're gifting as of the day. Kimi, he, or the $2 cash. Ube's a player.
Here's the equator. Okay.
Where we thought of.
So Brian, can you read me the definition of latitude once again?
Aston, that you're 4 months.
Degrees north or south of the equator.
You're doing a UV. Not that you're 2 months, 6 days, that you're prime.
So
And you think you're prime.
Somebody
check this out. Wait, hold on. The TV in the background is kind of messing with me.
Yeah, it's distracted.
Can we not TV? Can you mute yourself, Mr. TV? I'll find Brian. Brian, I had to mute you because the TV. No, it's Alex. Alex, bad, Alex. If you're watching TV, you're not watching me. All right. Let's hide the trolls again. So Brian, I think you can unmute yourself if you want, Brian. I don't think you were the problem there. So in other words, what I was trying to say to everyone is, by the definition of latitude, that's your latitude. It's your degrees. Let me go full screen here. It's your latitude is your degrees north of the equator in our case. So now does that help you? Which angle should this represent on your sky?
Is the beta?
Exactly. And you can see that because if your latitude is your degrees north of the equator points towards the celestial equator and your head points towards the zenith. So now that you can see Earth and the sky on the same picture, you can see that this is your latitude.
Now that I can see it full, like the full circle, it makes more sense to me.
Yes,
Versus the
exactly.
half circle.
Originally, it's just the tilt of the way the celestial equator is lined up on this picture. You kind of have to look at it as an angle as opposed to looking at it flat. And
Nick,
that's what I struggled with in the beginning.
Nick, let's remember why I'm doing this. This is actually what it looks like for our local sky, right?
Mhm.
So, and Sabrina, the problem is you're standing on a circular Earth, right?
Yeah.
But when you step outside into your backyard, it doesn't feel like you're standing on a circular Earth. It feels like you're on a flat plane.
Yeah.
So we need to be able to translate between
Okay.
these two things, and it's difficult. And the reason why it's tilted is because it's tilted in our own sky. And I want you guys to get used to that, okay? Okay, so let's try another sample problem here. One of these angles represents the altitude of Polaris based on the definition of altitude. So you might want to read altitude out loud again to remember what that means. What is altitude?
Degrees above the nearest horizon.
Okay, so Nick, take a guess. Which angle would represent the altitude of Polaris?
I'm not sure.
Okay. Anyone else think they know? Mia, Mariah, Kiana?
Is it delta?
Very good, Mia. How did you figure that out?
Well, I figured that the north and south line was going to be what we're calling the horizons, since the little guy's standing there. So-
Can I clean that up just a little bit,
Yes.
Mia? I was actually hoping someone would say that. Mia, this is not the horizon. This is the ground. If I want to get technical with you, and you know I do, right? The
Yeah.
horizon is a ring that's wrapping in and out of the plane of the board. So technically speaking, it's not that the whole line is the horizon. It's that this point, that's your northern horizon right there, right? And this point here is your southern horizon. Do you see the slight difference that I'm saying? Basically, you had the right idea, but I just don't want you to think that this is the horizon. I want you to think that this is your northern horizon and that's your southern horizon. Does that make sense?
Yeah, I was just using it as like a base to like figure out which
angle,
like
right.
where.
Okay, so sure, I'm making a mountain out of a molehill. So you argued that if altitude is your degrees above the nearest horizon is the northern horizon, and so this angle is altitude, correct?
Yes.
All right. Now let's put in some numbers for the Rhode Island local sky. So far, we've just been general, but now I want to turn this into a 2D view of the Rhode Island local sky. So Mia, what is the latitude of Providence, Rhode Island?
That's a great question. Wasn't it 41.5 north?
Well, 42 degrees will do just fine, okay? So in other words, if this is your latitude, this angle is 42 degrees, okay? Now, isn't it true that there's a 90-degree angle? Where's my other, oh, here's my other meter stick. Isn't it true that there's a 90-degree angle between the celestial equator and the North Celestial Pole, right?
That makes sense.
So if beta is 42 degrees, what would gamma be then?
48.
48, excellent. Let's write that in as well. Now, I spy with my little eye another 90-degree angle. Isn't it also true that there's a 90-degree angle between the zenith and the horizon, right? So what would that make delta?
42 degrees.
Exactly. Let's write that in as well. I didn't leave myself a lot of room, so I'm just going to do that. And for completion, because I know this is going to be useful later on, what will alpha be?
48 degrees.
Excellent. Remember earlier that Brian suggested that delta was our latitude. It turns out that Brian was right. The altitude of Polaris is always equal to your latitude. And that's not only true in Providence, Rhode Island, it's true everywhere you go on Earth. This is why the North Star is used as a basis for celestial navigation. If you can measure the angle of the North Star, you know where you are on Earth. This is such an important point that we're going to take it as a note right under here. So follow along with me. I'll erase this Earth. We have just proved an important result, and the result goes a little bit like this. The altitude of Polaris is equal to your latitude. I think you should put a box around this because you're going to discover that many problems can be answered. We can figure out the answer to many problems by remembering that rule. The altitude of Polaris is equal to your latitude. So if you guys want to look at, I don't know if the sky is going to be clear tonight. What's my phone say? I've got this app and it'll say observing conditions will be clear tonight. The stargazing conditions tonight will be fair. If you want to see Polaris, take out your compass app, point yourself north, and go about halfway up the sky, 42 degrees, and you should see Polaris there. This is also a nice test of the horizon system, okay? We're going to get some more practice with that when we get to our homework today. At this point, I want to sort of slowly transition to thinking about orbits. I've got about 25 minutes to do that. So I think we should be okay. Let's think about the number of objects that we can see on our local sky at night. So tell me some things. Tell me about some astronomical objects that you can see with your naked eye. For example, the sun, right? What else?
Moon.
The moon?
Stars.
Stars?
Constellations, do those count?
Well, let's call stars and constellations the same thing.
All right.
So we can see stars.
I don't know if that counts for anything.
Yeah, clouds, true. Those are annoying to astronomers, so we're going to pretend like clouds don't exist. What about the astronomical? Although, believe it or not, clouds are a serious issue in astronomy. I can't tell you the number of times I've woken up all my friends at 6 a.m. on a Sunday so they could go see some eclipse. And they all show up sleepy-eyed, and then the clouds cover it, and they're like, Brendan, we hate you. So clouds are an issue for us. So we have the sun, the moon, and stars. What else?
Planets.
Good, Tegan. Tegan, do you know how many planets can be seen with the naked eye alone? You can start thinking about some of the ones you could see.
5.
Exactly. Tegan, you are correct. There are 5 naked eye observable planets. We call them like the 5 planets of classical antiquity or something. And you can see sometimes they even all appear in the sky at the same time. The 5 planets that can be seen with the naked eye are Mercury, Venus, Mars, Jupiter, and Saturn. So let's give this a think. If you were an ancient astronomer, or if you were like a farmer in Mesopotamia and you kept track of the motions of the stars, in addition to stars, you can see the sun, the moon, and Tegan says 5 planets. That's a total of 7 astronomical objects that are not stars. And check this out. There's also 7 days of the week. Coincidence? I think not. That's because the sun is for Sunday and the moon is for Moon Day. And Mars got associated with the German god. Oh, a little noisy back there. Let's mute you, Sabrina. Sorry. Okay. Mars got associated with the German god Zutag, and that became Tuesdag, now Tuesday. Mercury was associated with the Viking Woden god, who was the traveling trickster. So Mercury got translated to Woden in Viking lore, and that became Woden's Day in Old English. Jupiter literally became Thor's Day, and Venus is associated with the love goddess Freitag, that's Friday, and Saturn is still Saturn Day, if you think about it. So isn't that wild? The reason we have a 7-day week is because there are 7 astronomical objects that are not stars. And in fact, while we're not going to go into all the nitty-gritty, you will discover that the more you look into timekeeping, every aspect of timekeeping is related to some cool astronomy thing. That's because the sky was the original clock, right? So the number of days in a year, the number of months in a year, the number of days in the week are all related to the rotations of astronomical objects. You might be surprised by that at first. You think, oh my gosh, I've never really asked myself why there's 7 days of the week, and I never would have thought it was connected to the number of planets in the sky. But if you think about it, timekeeping is important to humans especially if you live in an agricultural society that has to know when to plant your crops, right? I mean, if you're a nomadic hunter, I guess you don't have to pay, you probably still paid attention to stars for navigation, and because, let's face it, there's no TV at night, so you got to look at something. You have to look at some blinky lights, right? So people paid attention to the stars, and they paid attention to the motions of the planets, and that was very important to them. They used the motions of stars and planets as their clocks and their calendars. And literally, if you think about the Romans, Jupiter was their god. Saturn, Mars, and Mercury were their gods. They weren't some abstract old man in the sky with a beard. They could say, I know where God is. Jupiter's right up there. I'm watching him move. Yeah, Kiana, you have a question.
Can you put the picture back up so I can write down the planets and the days?
Oh, yeah, sure. I'd be
Thank
happy
you.
to do that. And Kiana, this isn't the most important thing. I just thought you guys would kind of, what I want to talk to you about is the orbits of the planets. And so feel free to write this down. But this probably isn't the most important thing. I just thought it would be kind of fun, a fun meditation point for us to start with. I've got a question for you guys. When you go out and you look at night, how can you tell the difference between a planet and a star? Let's actually take that as notes, Kiana. I think that's a little more interesting. Can I erase this, everyone? All right. So I want to quickly discuss with you, and I have to not get carried away here, the orbits of planets, but how do I know it's a planet? Because after all, guys, when you look at planets with the naked eye, they just look like stars, right? Can you guys think of some ways you might tell the difference between a planet and a star?
Planets move differently.
That's the most important part, Tegan. In fact, I'm surprised that you started with that one. Here were the things that I was thinking about, and let's get to Tegan's in a second. First of all, they are brighter. Usually when people say to me, hey, Brendan, I saw this really bright object just after sunset. What? And I was like, Venus. You know, usually Venus is very, very bright. They are brighter. Here's another rule of thumb that astronomers use. Stars twinkle, but planets don't. Stars twinkle, planets don't. Even if those two things are true, it wouldn't be obvious to you that a planet was different than a star. You would just think it was a brighter star that doesn't twinkle. The real reason is Tegan's reason. Planets wander with respect to the background stars. Planets wander with respect to the background stars. And in fact, the Greek word planetos, something like this, is Greek for the wanderer. Wanderer. What's really interesting about the wanderings of planets is that it's kind of screwy on your sky. And let me explain what I mean by the wandering of the planets. On a single night, you don't notice the wandering. Because on a single night, Mars would be, say, let's say this red dot is Mars. Mars will be fixed to some particular location on your sky, like right here. So on a single night, this, by the way, is called the teapot. It's part of the constellation Sagittarius. So if you watched Mars on a single night, you would see the teapot Sagittarius rise in the east and set in the west. And you might notice that, oh, Mars is kind of near the spout of the teapot. But if you went out the next night and you looked for Mars again, you would see that Mars had shifted a little bit with respect to the teapot. And at first you'd be like, wait a minute, wasn't it over there the night before? I must be going crazy. Then you go out the night after that and you see Mars has moved again. And if you're a person who's been watching the sky, you'd say, okay, something's going on here. This isn't an ordinary star. not only is it wicked, wicked bright, not only does it not twinkle, but night after night, Mars is drifting eastward with respect to the stars. And that would be significant because you don't see any of the other stars doing that. They're kind of locked in place. What was very maddening for the Greeks was that not only were planets wandering with respect to stars, but from time to time, they did something very bizarre. For a period of about 2 weeks every year, the planets stop drifting eastward and they change direction and they start wandering westward for about 2 weeks. And then they change direction and they wander eastward again. This motion that planets go through is called retrograde motion. So if you hear those, dinguses saying, my Mercury's in retrograde, they're talking about the fact that Mercury is currently undergoing a retrograde loop. It's not that big of a deal, okay? It was a big deal for ancient astronomers because remember, if you were a Greek or a Roman and you were a polytheist, Mercury was one of your gods. So it probably troubled them to see their gods changing their mind and drifting backwards. And it's sort of like, I'm going this way, then I'm going that way. The Greeks probably thought their gods were crazy because they were constantly changing their minds about which direction they wanted to move. Perhaps that even contributed to the Greek irreverence for their gods. People worried about this for thousands of years, trying to figure out what the gods were up to. And I don't have time to tell you the whole story, but it's a really interesting one. Eventually, Nicholas Copernicus, figured out the solution to what was going on. Copernicus realized when he placed the sun at the center of the solar system that he could explain retrograde motion as a natural consequence of Earth drifting past planets in its orbit. So this picture tries to explain why planets do the retrograde loop. First, you're kind of on Earth, and Mars is over here, and you see Mars somewhere near the Sagittarius teapot. And as Earth starts catching up to Mars, at first it looks like Mars is drifting to the left, which is eastward. But when Earth starts to pass Mars, it's just a geometry or a perspective effect. Suddenly you catch up to Mars, but Mars seems to be suddenly drifting backwards or westward relative to the background stars. And then as you continue to move forward, Mars will go east again. This is an effect, an optical effect that's called parallax, and it's going to play a pretty big role in our class. Let's all try out parallax really quick. Take your arm, put it out at arm's length and hold your thumb up. And now I want you to blink your eyes back and forth and tell me what you see your thumb doing. You can see your thumb shift with respect to the background, right? That's called parallax. That's not the last time we're...
We're gonna look really stupid on the recording, I'm telling you that much.
That's part of the idea, actually, Sabina. I wanted to have a good laugh later. That's okay. We can look stupid. That's, you know what? Maybe we'll look smart. Who knows? Okay, because we understand retrograde motion. Okay. That was pretty cool that Copernicus put the sun in the center of the solar system because he was the first person to kind of get a sense of how the planets were moving. One of the reasons people didn't accept Copernicus's sun-centered solar system is that Copernicus couldn't really predict the positions of the planets that well, and people thought he didn't know what he was talking about. The problem with why Copernicus had some errors in his positions is Copernicus was biased into believing that the orbits of the planets were perfect circles. And it wasn't until 100 or 2 years later that this German astronomer known as Johannes Kepler was trying to make the Copernican solar system work so he could predict the positions of planets. And he had a eureka moment where he realized, what if the orbits of planets weren't perfect circles? What if they were ellipses? And then all of it clicked together because he could suddenly make a model of the solar system that would predict exactly where the planets would move. So this is where we're starting in our class, because we kind of want to go forward from there and figure out how stars move, but everyone needs to learn Kepler's laws of planetary motion. They're like a really important foundation for astronomy. So to break you into it gentle today, first I want to talk to you about what an ellipse is. And then the second thing I want to do is teach you Kepler's laws of planetary motion. We need them for our homework today. So let's see how I'm doing on time here. I've got about 15 minutes. I think I can do this if I'm efficient. So first things first, let me let me get a picture of an ellipse for you guys. I'm actually going to go to my, I think my 1010 slides have a slightly better picture. History of astronomy. By the way, in my solar system class, I have a really intense lecture on the history of the solar system. My 1020 class doesn't really go into it. We just kind of have to do Kepler's laws. That's the story here. By the way, our labs next week, can you guys get a couple of things for me during the weekend? If you want to do the lab right on Tuesday, we're going to make models of an elliptical orbit in our lab. And the way you do that is you take a piece of paper and you put it on some cardboard and you put 2 thumbtacks into the piece of paper here and here. And then we're going to tie a little loop of string around the thumbtacks. And you put your pencil into the loop of string and you hold it tight. And then you drag around the paper and a beautiful ellipse comes out. So here's some thoughts for next class. Because I know what's coming, I have a little box of thumbtacks and a little loop of string. So if you think that's something you can find around the house for next Tuesday, if you see some thumbtacks and put them aside, we're going to want them on Tuesday, okay? If you can't get it together, we'll deal with it, but it would be cool if you could do this with me, all right? Okay, so we're going to make a cheap model of an ellipse right now, and the diagram that I'm going to base this off of is this one right here. So I'm going to show you how to make a quick and dirty ellipse. We need to have a major axis, a minor axis, and what are called the focus points. So draw along with me. Your ruler would be helpful here. So this is a diagram of an ellipse. Our technical definition of an ellipse is going to be a squishy circle, okay? And here's how we're going to draw that. We're going to make a line, make it about 10 centimeters or so on your page. Mark the midpoint. And now we have to make a vertical line that's shorter. So maybe make that one 5 or 6 centimeters, whatever seems right. So make a line that is distinctively shorter, and then just try to connect the edges with an oval. Like I said, we're going to make a better one next class, but this will do for now. So basically just kind of draw a football shape. Mine kind of looks like garbage, but we'll do it better next time. Let's mark off 2 focus points that should be equidistant from the center, F1 and F2. These are what are called the focus points of the ellipse. Mine were supposed to be equal from the center, but I'm doing this kind of sloppy right now because I'm rushed for time. All right. An ellipse has a couple of key parts to it. It has what's called a major axis. It has a minor axis. And there are a couple other parts we need to know about. This here, this distance from the center to the very edge has a unique name. It's called the semi-major axis. And I'm giving it its own letter here, letter A. A is the semi-major axis. It's going to turn out to be a very important property, a very important parameter in our class. This is not the last time you'll hear about that. The distance from the center to the focus point on either side, I use the variable x, and it's like called the focus offset or something like that. The focus offset. For different ellipses, the focus changes, and that's what makes ellipses different sizes and so forth. next class, we'll work on this a little more so you'll have more time to understand it. There is a parameter that determines how squishy your ellipse is. It's called the eccentricity. So let us define E as the eccentricity of the ellipse. And what the eccentricity means is it means the percent squishiness of the ellipse. And you can actually calculate E based on X and A. The eccentricity of the ellipse is X divided by A. That's an important formula. Because eccentricity is percent squishiness, you guys know that percentages are a number between 0 and 1. The domain of eccentricity, the domain of E is 0 or above, but always less than 1. So I'm using our math inequalities here. E can be equal to 0 or greater, but always less than 1. And the rule of thumb is that if E is 0, your ellipse is a perfect circle. If E is 0.5, it looks like an egg. And if E is like 0.9, then it looks like a cigar. So that's the, and I'm going to show you a picture of some different eccentricities. But that's a quick cheat sheet. Now I'm going to be throwing a lot of shit at you right here in the last couple minutes, so hang on to your hats.
Oh, I can't see the rest.
Okay, so yeah, let me give you a moment to catch up.
I got it.
Okay. How's everyone else doing? You need a second here, Sabrina? Mariah's good.
Yeah, like 2 seconds.
Yeah, yep, take your time. We're actually going to be using this in our homeworks today, which is why I'm trying to squeeze it in at the end here, because it'll be easier to do our homeworks and it'll go faster if you've seen this. Sabrina, give me a thumbs up when you're all set. Sabrina, you're good? All right. I'm erasing now. Oh, wait, no, before I erase, let me show you a nice illustration here. Let's just go to Google for a quick second. And let's just type in, I just want to type in eccentricity. And there's a little, this is what I want. It's not a great diagram, but it kind of gives you a sense. I want to just show you guys, this is what some different ellipses look like of varying eccentricities. On the left-hand side, a circle is technically an ellipse. It's an ellipse with 0% eccentricity. As I go to 0.2 to 0.5 to 0.8 to 0.9, notice I get more oval shaped and my orbit becomes more eccentric. Right here, I'm trying to point out to you guys that the orbits of planets and comets and stars, they can be circular. They can also be really extreme and very eccentric. It tends to be that comets have very, very eccentric orbits. Like, for instance, let's see if we can call up an orbit of Halley's Comet. Let's see if we have a picture drawn out. Yeah. So relative, this is one of the issues that the original astronomers had figuring out what the orbits of planets were like. They didn't really consider things like comets to be proper planets in our solar system. The orbits of planets are actually really, really close to circles. So people like Copernicus thought they were perfect circles. But they didn't contemplate the fact that maybe comets were also going around the sun for the same reason. They didn't have the idea of gravity. You can see that Halley's Comet has an orbit which is really, really eccentric. The importance of Kepler's laws of planetary motion is he was able to make a connection between orbits like this and orbits like this and realize that they were part of the same sort of system, the same sort of orbital system. So let's go ahead, and for our last thing that we're going to do today, I'm going to give you Kepler's 3 laws of planetary motion. We need them for our homework, so let's just bang them out. And then we'll take a tea break. Whoops. Introducing one of the great works of Kepler in his book Harmonious Mundi. He published in like 1642 or something what are called Kepler's laws of planetary motion. Every astronomy student needs to learn Kepler's laws of planetary motion because they're one of the foundational bricks for learning about cool stuff in space. The first law is called the law of ellipses, and it goes a little something like this. A planet orbits the sun on an ellipse with the sun at a focus point. A planet orbits the sun on an ellipse with the sun located at a focus point. I can throw that in there. I can feel the water returning to my brain. Guys, while you're writing that down, let's just look at a picture of that really quick. This is a picture of what that law states. The planet is orbiting the sun at an ellipse, but also notice the sun is not at the center. The sun's located at one of those focus points. It's kind of showing us that the sun is kind of offset, okay? Believe it or not, we're going to be able to calculate the perihelion distance and the aphelion distance in our class today. I'll show you how to do that in a minute. Let's talk about Kepler's second law of planetary motion. The second law tells us how the planet travels around the sun with time. It tells us that the planet's motion is not uniform, but it speeds up when it's close to the sun and it slows down when it's far from the sun. The way Kepler decided to express that is in the following way. A planet will sweep out equal units of area in equal intervals of time. So in other words, Kepler figured out that if it takes 2 weeks for Mars to go from here to here, later on, Mars would only go from here to here in 2 weeks. And obviously, this is a very long distance, and this is a very short distance. But he found that something was the same. If he made a line connecting the planet and the sun, and he counted up the little area boxes of this short triangle, it had the same exact area as the boxes in this long triangle. Let's write that down together. This is sometimes known as the law of equal areas, or I'm just going to abbreviate it as the law of areas. And it goes like this. A planet sweeps out equal units of area in equal intervals of time. The last law is actually the one that we need most for our homework today. So I've been building up to this. The third law of Kepler is a math formula. It relates the period of the planet, how long it takes to go around the sun, to the distance to the planet. It's known as the harmonic law. The harmonic law goes like this. P squared is equal to A cubed. Kind of pig piled those on top of each other. Let me write, I don't like the way that looks. Let me write it better. P squared is equal to A cubed, where P is the orbital period in years, and A is the average distance in astronomical units. Believe it or not, it was Kepler who invented the astronomical unit. He measured all the planetary distances in units of the Earth's distance from the sun. You could think of Kepler as the first person to figure out how big the solar system was relative to the orbit of Earth. So that was pretty cool. I'd like to try a sample, but we're going to do it. Okay, I'll tell you what. Because I do have to be conscious of time with you guys, because you have other stuff going on in your lives. I've used up all the time for my lecture. Now, we definitely need to practice this, but we're going to have 2 homework problems based on that. So why don't we just practice it as part of our homework? Is that acceptable to everyone? Kind of kill 2 birds with 1 stone? All right. I bet you guys would like a little tea break before we do the homework. Are we all into that? Yeah, I could use it too. So let's take a little sandwich break or something for 15 minutes or so. It says 1:30 on my computer clock. It says 1:37 on my iPhone. Does it say 1:37 on your iPhone? Okay.
Yeah, it's 1:37.
Yeah, I've got to figure out I keep starting class on my computer time, and that's probably messing you guys up because it seems even later. So I'm going to try to at some point sync these 2 up. Just forgive me for now. So if it's 1:40, let's say at 1:55 we'll commence homework. Deal? 1:55 by iPhone time? Okay. All right, so I'll see you guys then. Don't let me forget to unpause the recording. Oh, yeah?
Could you move the camera down a little so I can get the rest of that?
Yep.
Thank you.
And I'll leave it paused there for you, Brian. I'm just going to
Thank you.
pause while I get some tea. Hey, welcome back, everyone. It's time for our second homework session. Homework 2 is going to be a little bit of an adventure. This is a homework that starts off intense and then it gets easier as we go. So the first couple of questions are a little wild, but we can handle them. We can do them together. Let's see here. Let's get our paper set up in the good way. Don't forget to put your name at the top so we don't lose track of you. First and last name. Hey, something I probably should have announced at the beginning of class. I don't think it's going to affect anyone here because you're all doing your homework, but I have to do verification of enrollment this week, I think. And anyone who has not turned any homework or any lab, if you've turned in nothing, I'm going to mark you as a no-show and you're going to be automatically dropped from the course. So unfortunately, the people that I need to get this message to are not the people that are coming to the class or watching even the videos later. They're the people who are doing nothing. So I might have to send out an email to the whole class about that, but I thought I'd mention it for the hell of it. You need to make sure you're turning stuff in.
I'm just hoping that everybody shows up to the lecture for the rest of the semester, so that way we can continue to do these live sessions because they're
right.
Like
so
a privilege.
If you guys are really, I thought that there might be some of you out there who would enjoy this. And so one of the reasons I put the 5-person rule is, believe it or not, Nick, I actually had a class where no one would share their video with me. And at that was like, not this semester, but it was like either the summer or something. It was a smaller class. And it was kind of like, geez, if no one's going to share their video with me, what's the difference between me talking live and me doing the recording, So I put 5 people as a rough number, but I'll try to work with you guys. If you're giving me the feedback that you really like this, you can show me, as you guys are, by sharing video and interacting with me, and I'll try to work on keeping it going. All right, so I'll work with you. We got our name, AS1020. Hopefully you guys have figured out what your section is. Let's put our section down. You're either in section 001 or 002,
Bless you.
Gesundheit, or some of you are in section 003. So figure out what section you're in and put that down. I can help you guys figure that out if you're having trouble. And then, of course, we're going to be doing homework number 2 today. Does anyone have there's going to be 5 problems, but they're from different chapters. Mateus, do you have the numbers there? Can you read them out to me?
I'll pull it up right now.
Some from chapter 1, some from chapter 2. No, some from chapter 2, some from
No,
chapter.
it's chapter 1, section 1.
No. Chapter 2, chapter S. Oh, there we go. Zach's typing them out. So chapter 2, number 59. Special chapter S1. Well, I lost that there.
I got 41 and 43 for that one.
Okay. And then from chapter 3, what do we got?
53 and 54.
Okay. All right. Andrew, are you down to read us chapter 2, number 59?
Yeah.
Let me actually say something before we get started here. How do I want to do this? The title of this, Andrew, is Eclipse Conditions, right?
Yeah, I found it.
Is the title Eclipse Conditions?
Yep.
Before you launch into it, let me just say something to start off. You guys will remember that in our last homework, we used a legendary formula called the small angle formula. And that said that the size of our star or moon is the angular size times the distance times 2 pi over 360 degrees. Let's write that down. In today's first problem, you're going to see a new variation on the small angle formula. And it's actually kind of a really big deal in this class, but I didn't have time to explore this aspect during our lectures. Sometimes you want to calculate the diameter of a star, like I think in our last problem, we had to calculate the diameter of Betelgeuse based on its angular size. But sometimes instead of calculating the diameter of the star, sometimes you want to calculate the angle of the star, the angular size of the star. And you can do that with the small angle formula if you rearrange it using algebra. I'll skip the details of the algebra, but you basically flip everything to the other side. And this is the same as the small angle formula, but you could think of it as calculating angular size. And this version of the formula is what we need for this problem. I like to write it like this. The angular size of your star or your planet is 360 degrees over 2 times pi times the size divided by the distance. So actually put a box around that, because this version of the formula, it's going to be pretty important. You're going to have to use it a lot in this class. And there will be problems on the test like this as well. So this is an important practice problem that we're about to do. Okay, Andrew, there's going to be a lot of words. This is a big problem. We're going to have to take down a lot of data. So Andrew, launch into it.
All right. All All right, so eclipse conditions, the moon precise equator diameter.
Wait, let me help you here. That word is equatorial.
Equatorial?
So start
yeah,
again, this time equatorial.
The moon's precise equatorial diameter is 3,476 kilometers, and its orbital distance from Earth varies between 3,560, 400, and
Can we try that
400,000.
again, Andrew? I think it's 356,400 kilometers. Is that right?
Yeah, 356,000. Yep.
Okay.
And then 400,006 kilometers. Oh no, 406,700 kilometers. The sun's diameter is 1,390,000 kilometers, and its distance from Earth ranges between 47.5 and 152.6 million kilometers.
Okay, hold on. 147.5 and 150.
152.6.
Okay,
million.
hold on a second. The sun's diameter is 1,390,000 kilometers, but let's put that in a scientific notation. That's 1.39. How do we do million in scientific notation?
It's
Times
times
10 to
six.
6 power.
6 power. Yep, you guys got that. So let's write that down. So 1.39 times 10 to the 6 kilometers is the diameter of the sun. Remember that we use S for the diameter. And then 147.5 million kilometers. 152.6. So actually, guys, what makes this a nice problem is we just learned that the orbits of planets are ellipses. It turns out that the orbits of moons are ellipses too. So for the moon, this is the closest approach. This is the farthest approach. For the sun, that's the closest approach that Earth makes, and that's the farthest approach. Let me tell you the names of these things. For the moon, we call the closest approach perigee, and for the moon, we call the farthest distance apogee. Do you guys remember what the terms were for the sun? What do we call the closest point in orbit to the sun? That's a vocabulary term. Someone's got to know it. No? Oh,
I think I found it.
what is it?
What's it called?
Yeah.
Oh God, how am I gonna pronounce this? Is it the purloin? Something like that? I can't pronounce it. I'm sorry. Yes. Perihelion?
Helion, perihelion. That's
Yes,
right.
that.
Peri means next to, Helios is the sun, right? So it's perihelion. And what do we call the farthest approach from the sun?
Aphelion.
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 So I'm teaching you guys a little vocabulary while we're doing that here, okay? Okay, now that we have all of our data down, Andrew, what the hell does it want us to do?
All right. All right. So find the moon's angular size at its minimum and maximum distance from Earth. So that's for A.
All right, I'm gonna have to erase this in a second, so make sure you have it down. While I'm waiting for you guys to copy it down, do you guys understand what's going on in this problem? What they're saying is sometimes the moon is close and sometimes the moon is far away. Let's use a moon globe. And the point they're trying to make is when the moon is closer to Earth, its angular size is going to be large. If it's a little farther from Earth, its angular size is going to be smaller. and we're going to calculate the changing angular size based on the distance, right? Okay, does everyone, Andrew, do you have all that copied down, or do you need a second?
So
Except for the sun.
All right, everyone just take a second.
so is that 356,400 kilometers is the angular size when it's closest,
Well, that's the distance at when it's closest.
distance when it's closest, and then the one underneath the 406,700 kilometers is the angular size when it's the furthest away.
My only critique with what you said is technically these are distances, and we are going to
Yeah.
calculate the angular size. But
Okay.
I understand what you're saying there, I think. But
And
yeah,
then that, sorry, I keep talking over you. I'm sorry.
that's all right. No, that's cool. It's a dialogue.
So the 1.39 times 10 to the 6, that's just the size of the sun. And then that's the same thing with the moon. Those two numbers is the distances.
These are diameters.
Yeah.
The diameter, which is fixed, and the distances are changing. So the moon and the sun will have fixed diameters
Mhm.
or sizes, but as their distance varies, it's going to affect the angular size.
Okay.
Yeah, that's fine. Can you just watch the video later and make sure you get that turned in?
I promise.
Okay, it's a really important problem set. So I understand you guys have work and stuff, but Godspeed, and we'll catch you on the flip side, okay?
Deal.
All right, bye.
Have a good day.
Yep.
I already got that all down, Brendan.
Okay,
you
I'm going to erase. I got to erase because I need the board space here, okay? Anyone else? Can I erase? Yeah. Okay.
Yeah, I'm good.
Okay, we're going to keep this nice and organized. Let's start with part A. For the moon, we're going to calculate first the angular size at the minimum distance. I don't know why I put a dash there. That was weird. So the minimum distance, we have the angular size is 360 degrees over 2 pi. The size of the moon is 3476 kilometers. Can you guys remind me what the minimum distance is? Because I erased all the data.
356,400.
Okay, write that down. We're going to have to talk about how we punch this into our calculator. It's tricky.
It's bigger. It's too small. So,
Okay. Let's talk about this before we try it, okay? What the hell is that sound effect?
That's like a phone. It's a phone.
Huh?
I think
Yeah, it's a phone vibrating.
Oh, it's a phone
Yeah.
vibration. Okay.
Yes.
I was
yeah,
like,
that
I
was my
was
phone.
getting
I was
contacted
like,
by
what the-
aliens or something. Okay. Let me explain why this is difficult and why people make mistakes. You have to consider your order of operations when punching into your calculator. Our plan is we're going to do the 360, then we're going to divide by 2, and then we have to divide by pi. Then we're going to multiply by 3476. Then we're going to divide by that distance. So let's sort of do it together here, clear it out. Let's start 360, divide by 2. Then we're going to divide by pi, just hit exp to get pi. Then we're going to times 3476. And then we're going to divide by the distance, 356, 400. And then we're going to hit equals. Hold this up. Show me that you got this number. Let me just look, everyone's, hold them up there. Everybody looks good. Awesome. Okay. Now, that's the answer, but how do we format it? What should we write down? Which of those numbers should we keep? Remember we talked about significant figures?
Is it the 0.5? So the 0.5, I'm assuming?
The 0 is not a significant figure, Sabrina. Sabrina, these numbers are sacred. They don't have measurements in them, but these are measurements. Can you
Okay.
guys tell me how many significant figures the top and bottom number have?
Four and six.
No, 4 and 4. These two zeros are not significant figures.
Oh,
Okay, that's how this works. 3, 4, 7,
Okay.
6 are all significant. 3, 5, 6, 4 are significant. So
I
if
have
we
sorry, I have a question. So if those zeros weren't there and we needed to figure out how many significant figures there were, would we just go by 4 because that's what the top number is? Does that make sense?
not entirely, to be honest. Here's why. If the zeros weren't there, do you mean the number would be this? Is that what you mean by the zeros not there?
Let's say it was like 356,465. Let's just say. So how would we figure out how many significant figures there would be there?
Okay. This number,
But it matched the
this,
top.
this number has 6 significant figures.
Mhm.
Now, in a situation, Nick, where you have mismatched precision, let's say the top number had 4 and the bottom number had 6, you would go with the shittiest number. So you would still reduce to 4. Okay?
Okay.
So
Yep,
in other
answers my
words-
question.
And now, if we're going to keep 4 significant figures, what should we round this to? Let's try that out.
5,000.
No. This is a
500.
number that's less than 0, less than 1. This number is 0 point, right?
Oh, so 0.59.
That would only be 2 significant figures.
So 0.59, 0.5588
That's good. And what are the units?
kilometers.
Check it out, Sabrina. Kilometers on top cancels kilometers on bottom. This is an angle. What units are left?
Degrees.
That's right. This is an angle. So 0.5588 degrees. Put a box around it. Now it's time to do the moon's angular size at the maximum distance. Class, will the angular size be greater or less at maximum distance?
Greater.
Less.
No, less. Remember, Sabrina, the smaller,
Smaller.
the
Yeah.
farther away you are, the smaller the angle. I tricked you. Okay. The angular size is 360 degrees over 2 pi times 3476 kilometers over 406,700. Is that what it was? What was it? All right.
Yep, that is.
406,700 kilometers. Okay, this time try punching it without my help and tell me what you get. When you get an answer, just shout it out.
I got 4.833.
Wait. You did not get 4. Did you get 4.8?
33, yeah.
Okay.
I got the same thing.
You guys did it wrong. All right. Let me tell. Yes, Mateus, that's better.
Think-
Let me tell you what they did. You guys hit times there. That's your problem. You missed something that I was explaining to you last time. You cannot hit times there. The calculator will screw up because it thinks you want the time. It'll think you want the pi on the top. You have to do 360 divide by 2, then divide by pi, then times that. So do it again. Divide by 2, divide by pi.
I got 0.4896 this time.
Good, but round better. You need to round it better.
0.49.
No, that's only 2 sig. I want the 4 sig figs. I just
Okay.
object to you saying 4896 when the number after 6 is a bloody 9.
So 4897.
That's what I want to hear. 0.4897. And what are my units?
Degrees.
Good. Box it up.
So we go 360 divided by 2 time, 360 divided by 2 divided by pi or multiplied by pi.
Divided by pi. Is that confusing to you, Sabrina?
Yep, and then you multiply
3476.
divided by 406,700,
Uh-huh.
right?
Yep.
And then, yeah. Okay, I like to keep track of that.
Yes, that's what I want you to do. And so
Okay.
the trick is, Sabrina, the first time you're doing this, it's awkward because you think you're supposed to times pi, but you
Yeah.
have to divide pi. That way the calculator knows it's in the bottom. Okay.
Okay. All right.
And
So
did
do
you
we
get-
technically ignore the multiplication in that 2 times pi?
No, you're missing the point. We're not ignoring the multiplication. The calculator,
Now again.
the calculator cannot see this equation, right? It
Mhm.
only knows what you tell it to do. If you type 360 degrees divided by 2, the calculator instantly computes that as 180.
Okay.
If you then say times pi, it thinks that you want the pi to be on the top. If you tell it divide pi, that means the pi is also on the bottom, like the 2.
Oh, okay.
Did that make sense?
Yeah.
So even though we're writing 2 times pi, from the calculator's perspective, pi needs to be on the bottom. So we have to hit divide by pi.
Okay.
I know that mistake is going to happen. That's why we're doing this, okay? We'll try it again a couple more times. Okay, now we have to do part B, which is for the sun. Can I erase here? Does everyone have this?
Yep.
All right. I'm going to save a little bit of marker space, and I'm going to kind of keep my structure here. You guys are going to have to rewrite it. So for B, we're going to take on the sun, and it's going to be the exact same setup, but the S and the D are going to change. All right. I believe the diameter of the sun was 1.39 million kilometers. So I'm going to put that on the top for both. What was the minimum distance?
$147.5 times 10 to the 6 kilometers.
Good. How about the maximum distance?
152.6 times 10 to the 6 kilometers.
Okay. Why don't you guys practice punching it in? Oh, by the way, Nick, you and I were talking sig fig stuff, right? How many sig figs are we going to keep in this problem?
5 or
Nope.
6.
Nope.
3.
3. The top number has 3 sig figs. The bottom number has 4 sig figs. We have to go with the crappiest number.
Mm-hmm.
All right. Punch them up, round your answer to 3 sig figs. Tell me what you get. Okay. What's the angle for the minimum distance?
I'm not sure where to round this one, but on the calculator, I got 0.5399.
Right, but we want three significant figures.
Yep. 0.540.
That's how you do it. Nice. That's three sig figs right there. Good. All right. How about the one below?
I did that wrong on the calculator.
What did you get?
A whole 195
Oh,
point
okay.
something.
All right,
So-
let's, Sabrina, there's probably going to be
So-
other people with the same issue. So watch me
Okay.
do it, okay? 360 divide by 2 divide by pi times 1.39. I bet I know what you did. You
I think
have
it's
to
this
use
part right here.
You have to use exp for times 10, right?
Okay.
exp6 divided by 152.6 exp6 equals. Sorry, I did the bottom one by accident.
Oh, okay. So let me try it. So
Yeah,
36.
Make sure you use exp when you see times 10.
Okay.
I got the answer for the second one.
Okay, read it out to me. 3 sig figs.
0.522.
Yeah, 0.522. Was that Brian?
Yes.
Cool. I just wanted to make sure I recognized the voice.
Well, you're doing
Sabrina,
a good
did you
job
get
at
that
it.
this time?
I did.
Awesome.
do the other
That's
one.
good. All right. Everyone got this? I'll probably need to erase for part C, okay? All right, here I go.
Hold on.
Yeah, sure.
Okay. I'm good.
All right.
Okay.
Hey, Andrew,
Yeah.
can you read me part C?
Yeah. So based on your answers to parts A and B, is it possible to have a total solar eclipse when the moon and sun are both at their maximum distance? Explain.
Okay. Nick, I want you to do me a favor, Nick, since we've been talking sig figs together. In order to make the problem easier to comprehend, I want you to give me the angular size of the sun and moon at maximum distance, but could you please round them to 2 significant figures for me? So what's the angular size of the moon at maximum distance rounded to 2 significant figures?
Whoops. I was talking, my mic was muted. So you want the max distance first?
The angle at the max distance rounded to 2
So
significant.
it would be, sorry, I always interrupt you. 0.49 degrees.
Wait, is that the max distance or min distance?
Max distance.
Oh, right.
Oh, maybe
No.
yeah,
no.
it should be.
You're
Correct me
right.
if I'm wrong.
No, you're right. I'm sorry. That's last night's whiskey talking there. I just made a mistake. Let's now try, Nick, the angular size of the sun at maximum distance. 2 sig figs.
At 2 significant figures.
Yeah,
0.52.
degrees, right?
Yeah.
Okay. Hi, Taryn. Are you just joining us? Oh, you've been here? You were trolling? Okay. Is that a kitty or a doggy? What's going on in the background?
This is my puppy.
Oh my gosh, that thing is cute as hell. Wait, I'm gonna full screen that. What's that little puppy's name?
This is Pippa. Oh my, sorry.
That's okay. Wait, did you say pickle?
This is Pippa.
Pippa.
Yes.
I like that guy. We want to see a whole bunch of him or her, whatever it is.
It's a girl.
Okay, cool.
But we can make that happen.
All right, okay. Yeah, don't be a troll if you've got cute dogs in the background. We want to see those things. Okay. So what do you guys think? At maximum distance, this is the angular size of the moon. That's the angular size of the sun. Can we have a total solar eclipse? I want to remind you guys what a total solar eclipse looks like here. It's where the moon completely blocks the sun. Total solar eclipse sort of looks like this, right? It's a pretty cool pic. I'd like the big version though. Oh, I really hate how Google, they don't let you just grab the image. Oh, you're gonna make me watch a fucking video. All right, here we go. Sorry, all right, you know what? You fail. Let's try this one. This is what a total solar eclipse looks like. So can I have a total solar eclipse when the moon and the sun are at maximum distance? What do you think?
I think it will be slightly I don't know. It might be slightly off.
Why
It might
would
not
it
be total. It'll just be like one of the, I forget what you call them. I think you brought one up, an image of it, but the sun is partially covered by the moon, but not totally.
Right. So there's two versions of that. There's a partial solar eclipse. A partial solar eclipse is when they're not aligned properly, so you kind of get a bite taken out of the sun by the moon. And the third type of solar eclipse is an annular eclipse. And an annular eclipse is when. So what do you think, Sabrina?
I honestly think it will be more of an annular, in my opinion.
Yes. Because, and the reason why, just, yes, you are correct. But explain why.
By them 2 kilometers is just, well, the ray is just off, just slightly.
It's off in angle. The moon's angular size is shrunk. Let's actually draw a picture of what's going on so everyone understands it. So here's the sun. The angular size of the sun is 0.52 degrees, but the moon, its angular size is a little bit smaller, and its angular size is 0.49 degrees. So it's a 0.03 degree difference. 0.03 degrees might not sound like a lot, but that's about 2 arc minutes, which is significant. Okay, so we're going to write down the following thing. No, a total solar eclipse is not possible because the angular size of the moon is 0.03 degrees less than the sun. And we'll add a bonus bit here. Sabrina pointed out instead you get an annular eclipse. So that teaches us the conditions under which an annular eclipse happens. Not only do you need to have an eclipse, but that eclipse has to happen when both moon and sun are at their farthest distances. Or at least the moon has to be at its farthest distance. I cover eclipses in my solar system class, But I do feel somewhat obliged to tell you guys on a fun note that there is an eclipse coming up a few years from now. I think we're going to have an annular eclipse. I was looking for it last night, but NASA has a solar eclipse page. It has a lunar eclipse page too. And you can look up the eclipses for a whole bunch of different years. I want eclipses for 2021 to 2030. And this is telling us the different types. Look at this, guys. 2023, that's 2 years from now, there's an annular eclipse that can be seen from North America. I wonder if this is the one. Let's click on it.
That looks interesting.
It looks there's a better version of this. I want the one where it's going across the US. Oops.
It's not necessarily seen at, these eclipses are not necessarily seen in the same place.
Right. So that's one of the issues with eclipses is not only eclipses don't happen all the time. They happen a couple of times a year. But Sabrina, you've got to be in the right place to see them. And believe it or not, some people will actually travel to great lengths to see them because they're beautiful. I think actually what I was trying to tell you is one of the eclipses is going to pass through like Vermont. I thought it was the annular eclipse, but it's actually a total eclipse. I think this is the one. I just wanted to tell you about it because, yeah, look at this. This is a few years from now. What was the date on this again?
2024.
And look, it won't hit Rhode Island, but I've been thinking about this, right? So this is 2024, which is 3 years from now. The eclipse will actually pass through upper Vermont in New Hampshire. And what I was thinking, guys, is we're pretty close. So it probably would be worth it to drive up to northern Vermont that day, assuming the skies are clear, just to see that. You could go camping. I even thought about trying to book like a motel or a hotel up there. I bet people are so crazy about this stuff. I bet all the hotels are booked up there on that day already. I bet even 3 years in advance, people have like totally staked it out.
But I was thinking, question.
Yeah, sure.
So since the eclipse is like pretty close to us compared to, you know, other places on the world that it could be, how come we can't see it? Or from like where we are, would it look different?
Yeah, so what it will look like to us is on that day, we'll probably catch a partial eclipse. So what'll happen for us, and this happened a couple of years back. I don't know if you guys remember, but there was a solar eclipse where from Rhode Island, we saw the moon kind of pass over a little bit of the sun. But of course, to go to the path of what's called totality, to see the complete eclipse, that's totally badass. Because if you're outside during a total solar eclipse, the daytime sky suddenly goes dark and like cows go home to roost and birds start freaking out and it actually gets cold. But what's really cool about total solar eclipses is I guess they're pretty beautiful for two reasons. The first is it doesn't go completely dark because you can suddenly see the eerie light from the sun's corona. So it kind of creates this weird magical twilight. Another thing that my astronomy professor friend was telling me, because he went to see it out in Wyoming, is he said, don't forget, if you look towards the horizon, you can see places on the horizon that aren't in the path of totality. So it's like nighttime overhead with an eerie glow, but then the horizon is glowing with sunlight. So it just looks really effed up and crazy. In fact, I guess it only lasts for about 5 minutes, but that 5 minutes is so cool that people get addicted to seeing solar eclipses and they'll like get more extreme about how far they're willing to go to see them. I've seen a few partial solar eclipses now, but I have never myself seen a total solar eclipse, and I feel really bad about that. And I want to see one. So I've been thinking, I'm notoriously awful. I hate driving and I hate going anywhere. But I was thinking if this one's going to pass through upper Vermont, that's only a couple hours. I should probably do that. So anyways, I thought I'd share that with you so it's in the back of your mind, okay? A couple of years from now, people will be you'll hear about it on the news. It'll be a thing. Okay, can I erase all this here?
No, I'm not
Right.
done.
Yep, take a second.
Isn't there an eclipse? I think it might be the solar eclipse that you have to wear like certain like glasses. Like I don't even know if that's like a real thing or if that's just because like there's an eclipse and people are like, oh, you have to wear these glasses to look at it. But like, what's that about?
It's a very real thing, and let me show you. I actually, of course, have a bunch, and sometimes I give them to students if I get extras. These are called eclipse shades, and what they are is they're basically like it's almost like a piece of foil that only lets in about 1/1000th of the sunlight through it. So this basically reduces the brightness of the sun by a factor of 1,000. And the reason why you need it is the eclipse only lasts for like a minute or two. And during the buildup, you're slowly blocking the sun. But you don't realize this, but the sun is so bright that you can actually burn out your retina and you can permanently blind yourself just by staring at the sun. Normally what happens is if you look at the sun quick, your eyes have a blink reaction, and without you even controlling it, your eyes will automatically shut because it's painful. But if you were crazy enough to keep your eyes open and stare at the sun, you could easily develop blindness. Famously, Galileo went blind from looking at the sun, not knowing any better. So the scary thing about the eclipse is, for a second, you're covering the disk of the sun and it would be safe to look at, but then your pupils are really, really dilated because it's dark and you're letting in all this light. And the moment the sun peeks back out, bam, you're going to hit your eyes and you're going to really mess yourself up. So astronomers and scientists are really intense about this because they want people to enjoy the eclipse and see it, but they don't want to make a bunch of people blind because of it. That would suck, right? So it's a serious thing. So that's not fake news. That's real stuff. And you got to take it serious. When I saw an eclipse as a kid, what we used to do is make a camera obscura. So you'd get a big printer box and you'd poke a little pinhole through it and put a piece of paper on the other side. And the sunlight would come through the pinhole camera and you could see the disk of the sun on a piece of paper. But I remember it was funny because all the kids are like walking around the yard with like boxes on their heads. Really funny. So camera obscura is one cheap way to do it. These things are wicked cheap. You can order them on Amazon for like 50 cents or something. Any science museum will have them, wherever you'll find them floating around.
Oh, wait, can I see the bottom of that?
Yeah, sorry, bud.
Oh, I got it.
All right, I'm going to erase this and we'll get on to the next one. All right, let's see here. Nick, are you down to read us a problem? How about chapter S1, number 41?
Yeah, I got to pull it up here.
Sure.
All right, so that's chapter 4. All right, I got it right here. Give me 1 second. So which one are we on now? I'm sorry.
Chapter S1, number 41.
Number 41. I think I may have the
There should be
wrong
three
one.
different. There's one for chapter 2, one for S1, and one for chapter 3.
Oh, I'm on chapter 4. That's why this isn't making a sense. So we're on chapter S1. 41. Fundamentals of your local sky. Does that sound right?
Yep.
Answer each of the following for your latitude. A, where is the north or south celestial pole in your sky?
Okay, so since we're in the northern hemisphere in Rhode Island, we're going to be looking for the north celestial pole. Can you guys help me remember the latitude of Rhode Island?
42.
42 degrees north. Okay. They want us to describe the position of the north celestial pole in our local sky. Students, what coordinate system do we use when we want to talk about the position of a star in our local sky? Which of the two coordinates do we want to use here?
Is it RA and D? RA and DEC?
Those are the equatorial system. And the reason why they're not as good here, Sabrina, is those coordinates are better for the global sky when you just want to know where they are on the globe. But here
Okay.
they're asking for us to say, where is it in our sky? Like if we're in Rhode Island, where would I have to look? So in that case, we'd probably want to use
The horizon system.
the horizon
Use
system. Let's write that down. We want to use the horizon system. And the horizon system has two angles, altitude and azimuth. And I want you guys to think about it. What is the altitude and the azimuth of the North Celestial Pole? So let me help you understand what's going on here. In today's slideshow, the local sky, slide 49, basically they're asking for us to describe the altitude and the azimuth of that point right there. Who thinks they know the answer? We learned how to do this in today's class, believe it or not.
Is that 42 degrees?
Which one are you giving me, altitude or azimuth?
Altitude.
Very good. And how did you know that?
To be honest, when we did that, I was gonna ask how you got those numbers. Like the 42, the 48 going from the alpha, the beta, and the gamma. I
Right.
wasn't sure how you got those degrees. So I'm just giving you what I wrote down from the board.
Okay, sure. Let me explain again how I got that. You'll remember that in a previous lecture, when I talked about geographic coordinates, I told you the latitude and longitude of Rhode Island. So you were already supposed to know the latitude of Rhode Island is 42 degrees. And if you don't believe me, you can just look it up on your phone, right? Okay. I also told you today that the angle between the celestial equator and the zenith, the beta angle, is the same as the angle between the equator and where you are on the Earth, right?
Okay.
My argument was the Earth's equator points towards the celestial equator, and your location on Earth points towards your zenith. So the way I got that angle is I already knew what my latitude was, and I realized that this angle was the same as my latitude, and then I knew that was 42 degrees.
So
And
this
the
was
rest-
actually like using our latitude, basically.
This is important. Yes, that's what we mean by local sky. Like what? Not what's up in anybody's sky. What's up in your mother effing sky from your position on Earth? Because remember, Nick, the reason why is it changes wherever you go. So there's not one answer. It depends upon your latitude. That's the key.
Okay.
That's why this title is Fundamentals of Your Local Sky. A dude in Rhode Island. Okay.
And I wrote that too. Okay.
Now, what about
Thank you.
Yep. What about the azimuth of the North Celestial Pole? Azimuth is kind of like direction. So this is kind of like what color is an orange, or who's buried in Grant's tomb? What's the direction of the North Celestial Pole?
North.
Yeah. It's in the direction north, but what's the technical azimuth of north? Do you remember? Azimuth is your degrees along the horizon measured clockwise from north.
90 degrees?
Nope.
Is that 0?
0, because
it's straight up.
Azimuth starts here, not straight up. Remember,
That's the zenith.
Azimuth is measured along the horizon. But since you're starting from north, it's 0 degrees. So we can have two different answers for the azimuth. Let's put them both down. 0 degrees or north. Okay. That's question A. Now let's tackle question B. Nick, when you're ready.
Right. B. So describe the meridian in your sky, specifying at least 3 distinct points along it, such as points at which it meets your horizon and its highest point.
So the meridian is actually an arc To describe an arc, we're going to need 3 points, and each point is going to have its own altitude and azimuth. I like to refer to the 3 points as the rise, the reach, and the set. So let's set this up. We're going to have a rise point. We're going to have a reach point. And we're going to have a setting point. And for each point, we're going to be obligated to give the altitude and the azimuth. So that's kind of a lot. Why don't we remember what the meridian is? Does anyone remember what the meridian is? Lots and lots of vocab in these early chapters.
It's the arc that rises due north and reaches your zenith that sets due south.
In other words, the meridian is this right here, this arc. So let's think about what we're talking about when we talk about those 3 points. I'll use, what color do I want? Yellow. Okay, this is the rise point. That is the reach point. And this is the set point. So let's start with the point in the north here. Can you guys give me the altitude and the azimuth of that point?
90 degrees.
Hold on, Sabrina, you need to tell me which coordinate you're talking about so I don't get confused. Are you giving me the altitude or are you giving me the azimuth?
I think that's the altitude, right?
Now, I remember the altitude as degrees above the horizon. So that point is not 90 degrees above the horizon, is it? Does that make sense what I'm saying, or am I confusing you?
Is it 0?
Yes. How did you know it was 0? Explain that.
In my head, I see it as it's the baseline. Like if if it's at that point, that's where I'm standing. That's where I can see it. It's like at the floor. So like it's not anything above the line.
Okay, that's okay, Mariah. Yeah. In other words, altitude is kind of like your degrees up, right? So if you're at the lowest point on the horizon, that's 0 degrees.
Okay.
But remember, Mariah, that's just your altitude. So it's on the horizon, so it's 0 degrees altitude. What would the azimuth be?
I feel like that's where I'm having trouble is the azimuth. I would still say in my head it's 0.
And you would be correct.
Oh, okay.
And that's because azimuth, remember, azimuth measures your angle along the horizon, but they start clockwise from north. So if you're on the northern horizon, your azimuth is 0 as well. Let's write both answers down. I want to drill into your head that azimuth is the same as direction. Azimuth is north, south, east, and west. You just put a number on it. Okay, now let's try the reach point. I need an altitude and an azimuth for my reach, and my reach point is up here. That's the highest it gets in the sky.
Would that be 90 degrees?
Which angle?
West? No, that's not the right
No,
answer.
no. Nick. The horizon system requires, Nick, let me make an analogy. Suppose we were in New York City and we wanted to get together for a beer. And I called you up and I said, Nick, meet me for a beer. I'm at this pub. And you said, where's the pub, Brendan? I said, it's on Fifth Avenue. Is that cool? Is that enough for you to find me?
No.
Because Fifth Avenue turns out to be really fucking long, and I could be anywhere along there. The only way you know where I am is if I give you some cross streets. I'm at Fifth Avenue and 42nd Street. By the same token, we're trying to find a pub on the sky, right? And our pub on the sky also requires two coordinates. We need an altitude and an azimuth. So when I said, tell me about this point, you said, is that 90 degrees? And I'm just saying, are you giving me the altitude or are you giving me the azimuth? I'd like you to specify.
The altitude.
Very good. I agree with that. The altitude of that point is 90 degrees. Okay, what about the azimuth? This is a nice tricky one. We might need Mateus or Andrew to help us with this. I don't know.
Which one is it?
What is the azimuth of this point?
Oh, it's at the zenith.
Well, it is at the zenith, but what's the technical azimuth?
0.
No. There's actually there's an issue here. There's a problem, but I'm trying to figure out if you guys see what the problem is.
It's off of the ground somehow.
Well, it's okay to be off from the ground.
But
For
there's
instance,
no, oh, I know what you mean. The problem is there's like no north or south.
right. So another way to say that is this point is equidistant from the northern horizon, from the southern horizon. Every single point on the horizon is equally far away from this. So there technically is no azimuth. Azimuth breaks down at the zenith because the zenith isn't, to have an azimuth, you need to be kind of close to one of the points on the horizon. Like when you're at the North Celestial Pole, you're definitely closest to your northern horizon, right? So that's your azimuth. But at the zenith, every point on the horizon is equally distant. So it's technically undefined. That was sort of a tricky question. So let's just put 2 dashes there. It's undefined. However, Andy pointed out that it's at the zenith, so we can write that. The azimuth of the zenith is undefined. Okay, guys, how about the setting point? Now give me the setting point. The setting point.
One more quick question. I don't want to hold you up anymore, but on the north side, you said that the point at the zenith was undefined, and you had wrote put a little blue dot kind of like on the northern horizon. What would what's the thing? What would the reach be if it was like in the bottom right corner on the northern horizon? How would we write that? If that makes any sense.
Nick, we're going to have to direct that question a little better. So let me see if I understand you. You want to know what the hypothetical altitude and azimuth would be if I was where? You can
Go
actually,
up a little bit more.
like here?
Like right there. Yeah, like right there.
Okay. Yeah, sure. Here's how I would do that. I would say it looks to me like the angle is less than 45 degrees. So I might say 30 degrees or 35 degrees altitude.
Okay.
As for azimuth, the azimuth is the point on your horizon which is closest to that location. I would argue that since it's on the meridian, that's the closest point on the horizon. So I would say its azimuth was 0 degrees. So my final answer for the blue point would be altitude 30 degrees, azimuth of 0.
So if it was on the southern side where that other blue dot is, that would also be 0.
Wait, are you giving, once again, Nick, we're looking for a pub. Are you giving me altitude or are you giving me azimuth?
Azimuth, I'm sorry. The
No.
azimuth would be 0 because
The
it's
azimuth is not 0 because
90?
azimuth is, yes, no, not 90.
180. It's 180 because it's half of that.
That's right. It's clockwise
Okay.
to the north.
Okay.
So what about its
now.
altitude? Its azimuth is 180, but what's its altitude?
Like negative.
Nope.
No, not negative.
Altitude is degrees above the nearest
0?
horizon. Also 0 because it's straight on the horizon.
Okay,
take
I
a
got
look.
you now. That was my confusion.
All right. So let's say the setting point, the south point is 0 degrees. and this is 180 degrees azimuth or south.
Thank you.
Sure. This question is really intense. I knew this question was going to really kind of cook your noodles. That's one of the reasons I asked it, to really kind of master this material. All right. I need to erase. Has everyone got that?
I got it.
Nick, what about part C?
I gotcha. Hold on one second. All right, see, describe the celestial equator in your sky, specifying at least 3 distinct points along it.
Once again, we're going to have a rise, a reach, and a set. For each point, an altitude and an azimuth. All right, let's look at our points again. The celestial equator is the red ring. I would say, considering that most stars rise in the east and set in the west, this is the rise, this is the reach, which is the highest point, and that's the setting point. So anyone who feels up to it, let's start with the rise point. I'm looking for the altitude and the azimuth of that point.
Is that going to be 0?
Which one? Which angle?
The altitude?
Very good, because it's on the horizon. So the altitude is 0. Excellent. How about the azimuth?
So, is it?
There's nothing to eat.
Got to get that youngster doing some astronomy.
Right?
Maybe he can help. I couldn't tell if it was a boy or a girl because it was.
Yes, she is a girl.
Oh, it was a girl. All right. You have the correct altitude, 0 degrees. Do you want to try the azimuth?
Okay. So the azimuth is.
It's clockwise from north. So how many degrees?
Is that also going to be 0 again?
Nope, because remember, I tried to draw it in yellow. The azimuth is your degrees measured clockwise from north. So you're looking for this angle right here.
So is that going to be 90 degrees?
Excellent, because it's quarter turn from north. Okay, so we can write for the azimuth either 90 degrees or east. Sometimes when people want to specify a point on the horizon, they'll use the term due east. Due east is kind of a classy way to say altitude 0, azimuth 90. You're just saying due east on the horizon. Like if you're on a boat and you travel due east, you're traveling towards the horizon in the direction of east. You can think of this as how high up, and this is the direction, okay? All right, now let's try the reach point. You guys are starting to get this, I can tell. The reach is here. Remember, this is for the Rhode Island local sky.
Is that going to be 48 degrees?
Very good. Sabrina, you are killing it. How did you know that was 48? I bet not all of your classmates understood that. How did you?
That's exactly how I bet based on this little thing that we drew up.
That's
and then
right.
from the distance between the two
That's exactly what I
is it
wanted
the
you to
same-
do. You used the alpha angle from the drawing that we made, right?
Yeah.
That's
Yeah.
what I wanted. So the altitude is 48 degrees. What about the azimuth? Remember, azimuth is the same thing as direction.
It's 180, right?
Correct, Mariah. And 180 is the same as south. Mariah, let's just understand what Mariah did there. She's recognizing that this is the closest point to that dot on the horizon. And then she's measuring 180 degrees clockwise from north. So we can write either 180 degrees, oops, or we could even say south. I would accept either answer. I'm going to put both down. Okay, and last, the set point. The set point is here.
Is that going to be 90 degrees altitude?
No, altitude is degrees above the horizon. You are currently on the horizon.
Oh, so is it 0 degree?
It's 0 degrees.
Okay.
It's on the horizon, so it's 0 degrees. How about the
So is it whenever it's on the horizon, it'll always be 0?
Correct, Kiana. I was
No
actually
matter like if it's on the south, north, as long as it's on that horizon, it's 0.
Yep.
Okay.
The entire horizon has an altitude of 0 degrees.
Okay. I wasn't sure about that, so I just wanted to clarify.
Mm-hmm. Kiana, while we're talking, do you know what the azimuth is?
Oh God.
How many degrees clockwise from north are you? So start here. What's 3/4 around a circle?
Oh God.
I did it on my calculator like earlier. It was like I got a weird number. I don't know if I did it right. It was like 270 point
70.
something degrees.
270. So
Yeah, I was about to be like, can I have a lifeline?
90, you can. Nick was 90 plus 90 is 180.
Yes.
180 plus 90 is 270. They call it the unit circle. You're supposed to memorize it. 270 degrees is the same as west. All right.
I'm afraid of a test.
Well,
I feel that.
Yeah, I can relate.
you should be. I asked you this question because I wanted to scare you, Sabrina. And here's the deal. This seems wicked confusing and crazy because the first time you learn it, it is confusing and crazy. And then at one moment, it all snaps into place and it's good. We have to go through these questions to get you to that place. There's another secret about the test, Sabrina, that's not obvious, which is as long as you show up and you do your homework with me and you do your labs with me, you can afford to really, really bomb the test and still pass this class with flying colors. So half the issue is if you're doing the homework with me, the test is going to be fine because you're going to remember some of this stuff. Some of it you'll get right, some of it you get wrong. But your grade's already going to be so high from doing all your homeworks and labs perfectly that it's not going to matter. So, of course, you want to stress out a little bit about the test because if you can do really, really well in the test, it'll vault your grade into the high A's. But you can easily coast through with a B or a C just by, even if you flunk the test, as long as you show up here. So it's not like there's no pressure, but oftentimes what makes tests so incredibly stressful is you're worried that if you fail the test, you will then fail the class, and then you've lost your money and you've wasted your time. I've designed the class so that even if you completely bomb the test, you will not fail the class. You will still pass, as long as you hang out with me and do the thing that we're doing now. So Sabrina, I'm not worried about you. I'm not worried about anyone who's here. I'm worried about the people who I haven't met yet that are doing bong rips on their couch and haven't even watched a single video. Those are the people that I'm worried about, okay? So Thankfully, you're here. You're doing it right. The struggle is real. All right. So,
Okay.
Nick, I'm going to erase this, and we're going to do part D now. There's like a million parts to this question.
Just to let you know, it is 3:10. I didn't know how many questions you wanted to do. I'm not in a rush or anything. I just wanted to
No, I
let
know.
you know
So
that I'm-
this homework, the next questions are going to go faster. This homework takes
All
a
right.
long time. This homework I knew was going to take 2 hours. So,
All right,
Nick, that point being taken, let's speed this up. So what's part
that's
D?
fine. So D, does the sun ever appear at your zenith? If so, when? If not, why not?
Okay, I'm basically just going to do this one for you to speed things up a little bit, but I want you to watch what I'm up to. I'm going to show you a picture of the path that the sun takes throughout the course of the year. I think I have it here. This is a crappy diagram, but it'll have to do. The sun travels the path of the ecliptic, and that means on any given day, like the sun will rise somewhere in the east, it'll come up overhead at noon, and it'll set in the west. Now, on the spring equinox, the sun is on the celestial equator. So and this is what our next question is too. On the spring equinox, the sun rises due east, comes up to an altitude of 48 degrees, and it sets due west. On the summer solstice, the sun is 23.5 degrees above the celestial equator. So it's going to rise a little bit north of east. It's going to come up to a maximum altitude of, let's think about this, from south to the celestial equator is 48 degrees. From the celestial equator to the summer solstice, that's 23.5 degrees. And if you add those two together, in Rhode Island, the highest the sun can ever get on noon on the summer solstice is a maximum altitude of 71.5 degrees in the sky. Now that's pretty high up there, but it's not at the zenith. The only places on Earth where the sun will reach your zenith are the so-called tropics. The Tropic of Cancer has a latitude of, wait for it, 23.5 degrees north. The Tropic of Capricorn has a latitude of 23.5 degrees south. Those are locations on Earth where the sun can reach your zenith. We're too far north. So let's make it quick and dirty. No, the sun will never reach our zenith in Rhode Island, but only a max altitude of 48 degrees plus 23.5 degrees is 71.5 degrees south at noon on the summer solstice. Just copy that down and you can think about it later. All right, I'm going to erase. Sabrina, you cool?
Yeah.
Hold on, I'm not ready yet.
All right.
So during the summer solstice, is that like the brightest day of the year, like the longest day of the year?
The longest day of the year, and also because the sun is highest in the sky, the sun is the most intense on that day.
Right.
So the sun kind of beats directly down, and it heats up the earth a lot. You would think
Okay.
that the summer solstice was the warmest day of the year, but the reason why it's not warmest is because of something called thermal lag. It takes time for the Earth to heat up. So it turns out to be that the summer solstice is when the Earth is getting the most sunlight, but there's a lag of about 1 or 2 months. So the hottest month of the year is usually August. It's a little bit after the
It's like defrosting at that point.
well, yeah, you're right.
Nice.
Yes. So or rather it's frosting. It's getting colder, right?
Okay.
Well, sorry, no, you're right. It is defrosting. It's going from cold to warm. Sorry. Your analogy
Yes.
was good. It was.
Yes. Okay.
All right. Can I erase? I'm doing that.
Yeah, you're good.
Oh,
So 48.
I'm
Yep.
sorry. Did someone say they were still working?
No, I'm good.
But you can erase.
All right. The next 2 questions are pretty tricky. What does E say?
Gotcha. E, what range of declinations makes a star circumpolar in your sky?
Do you guys remember what circumpolar means?
I don't.
Circumpolar stars never rise or set.
Oh, that's right. They're always in the sky.
Right. I'm going to kind of walk you through this one. It turns out that the faster I give you answers, the less you're going to like it because it's going to feel disorienting to you. Remember that the circumpolar stars are kind of doing this. They're going around Polaris.
Mhm.
Polaris is circumpolar, and the stars that are circumpolar will be stars that go all the way down to your northern horizon. The last circumpolar star will grace your northern horizon. Now, they're asking not for altitude and azimuth, but for declinations. Remember that the equator is 0 degrees declination. The north celestial pole, where Polaris is positive 90 degrees declination. And if you remember that the celestial equator extends down through here, the declination of your northern horizon, this angle is 42 degrees. So this angle is positive 48 degrees above the celestial equator. So in other words, let me show you the picture again. They're asking us, where's those circumpolar stars? They're asking us, remember how we counted the rings here earlier? We did declinations of the rings. They want to know which rings are going to be circumpolar. And the ring that's not shown here that touches the north is positive 48, all the way up to positive 90. Normally, I spend a long time walking you through this, but as Nick pointed out, it is getting late in the day, so we kind of need to move quicker. So it's positive 48 degrees, and the declinations are between that and positive 90 degrees. They also explain this a bit in the book. Question F asks for the opposite. They want the so-called anti-circumpolar stars. That's what I call them anyways. And the idea is, in Rhode Island, there's a range of stars that we can never see in the southern hemisphere because we're too far north to see them. And if you imagine that that slide I showed you is for our location, this is slide 81. Notice that if you have a local sky that looks like this, there are some stars, namely the yellow ring stars, that even as the Earth spins, they never actually come up above our horizon. That's actually really sad because there's some really cool astronomical objects that you can only see from the southern hemisphere. In particular, what I've always wanted to see is in the southern hemisphere, there are 2 galaxies that you can see with the naked eye called the Large and Small Magellanic Clouds. And it really pisses me off that I've never been able to see them with my own eyes. So I'm not much of an adventurous type, but maybe I should go to Australia or to South America at some point just to see this. Now, the range of declinations would go from the south celestial pole, which is negative 90 degrees, all the way up to stars which just touch the southern horizon, and that's negative 48 degrees. So it's basically the opposite of the original question. It's minus 90 degrees to minus 48 degrees. I'm not expecting that to make you guys feel good because I kind of did that a lot faster than I should have, but I'm balancing speed versus learning. And up to now, I've been focusing on the learning. Now I've got to focus a little bit on the speed. All right. Let's crunch on. I'll try to push us through. Okay, 43. Mateus, read it out.
All right, so 43, local path of the sun. Describe the path of the sun through your local sky for each of the following days. A, the March and September equinoxes.
Okay. So
spring and fall.
Equinox. We're going to describe the path of the sun. Just like before, we're going to have a rise, a reach, and a set. Altitude and azimuth. Let me do this one with you so that you can get the swing of the thing. On the spring equinox, the sun will travel the path of the celestial equator. I have a better 1010 astrometry. And even though they kind of twisted the angle a bit, I really like this picture here. This is a little jazzier than the last one I showed you. So the sun will travel the path of the celestial equator on the spring equinox. It's going to rise due east. It's going to come up to an altitude of 48 degrees. Remember that from the alpha game that I played with you, that 48 degrees is the altitude of the celestial equator. And then it will set due west. So the rise is 0 degrees. And here, instead of azimuth, we'll just do east. The reach is 48 degrees south. And the set is 0 degrees west. Mateus, part B.
The June solstice. I don't know if it worked or not.
That's
Man.
the summer solstice. So what's the altitude of the rise on the summer solstice?
It's 0, right?
0. And what I'm going to do for the azimuth is I'm just going to cheat and I'm just going to say north of east. Okay. 0 degrees north of east.
Just information on letter A, it also specifies the September one. Are you going to do that eventually, or?
The spring and the spring equinox and the fall equinox are the same.
Oh, okay.
So yeah, I should have probably explained that. Mateus, remember that, do I have a picture here? I've got a picture somewhere. Come on. Remember that the sun is on the celestial equator, not only on the spring equinox, but also on the fall equinox. So it's basically the same for the spring and fall equinox. Does that make sense?
Yes.
If you're on the celestial equator, you're just traveling the path of the celestial equator. Okay, what's the reach on the summer solstice? Here's a hint. We just did this. How high will the sun get on the summer solstice?
71 degrees.
Yep. 71.5 degrees south. And then it will set back at 0 degrees north of west. Okay. There's parts A through D. Let's just do part C and then we'll stop with this question. So Mateus, part C.
The December solstice.
Okay. So let's see what you guys have learned.
Oh, I need that.
Okay.
Brendan,
Yep.
I need that.
So I can repeat them to you if you
Yeah.
want me to.
All right.
So for the rise, the altitude is going to be 0 degrees. For the reach, altitude is 71.5 degrees. And for set is 0 degrees.
71.5. And what was the other one for set?
For set is 0 degrees. And then for the azimuth, it's going to be north of east.
North.
For rise, reach is south.
Reach is south.
And then set is north of west.
North of west. Thank you.
Sorry about that, Andrew. I'm trying to speed things up here because I know.
Yeah, I'm trying to keep up, but I'm sure. Yeah, never mind.
I goofed off a little bit too much during this office hour here. Okay, can you guys give me this last one? I want the altitude and azimuth of these 3 points. Anyone?
All right. So for the reach, it's going to be 0.
No, hold on. Whoa. Let's start with the rise. Start here.
Oh, no, for the rise. That's what I meant, not the reach.
Okay. So 0 degrees altitude, and it looks to me like we can just call it south of east. Okay. I thought it would be really cool if you guys could figure out the reach, the altitude of the reach. Do you guys know what this angle is here? And here's a hint. Let's look at it kind of edge on the way we did in our drawings. You guys are supposed to know the angle from south to the celestial equator. You know that the sun will be.
Is that 48 degrees?
Pardon?
Oh, no. Is it 48?
That's
It looks
48. So this is
Okay.
48 degrees, correct. But on the winter solstice, which we just passed, the sun is 23.5 degrees below the celestial equator. So do 48 minus 23.5. What does that give us?
24.5.
24.5 degrees. and that's south. And then the set will just be 0 degrees south of west. We're skipping part D. The last two problems are really quick, guys, so we'll be done soon enough. Bear with me. I'm sure whoever's watching this video later is going to get all kinds of pissed off. Then again, I suppose you could try to do your homework by yourself. Good luck with that.
Yeah, let's see.
I will say, like, one of the last labs that I had missed, I went on YouTube and it was 3.5 hours. I'm like, oh man.
Yes, it's not the same. It's not the
Yeah.
same. I did that too.
Yeah.
Well,
All right.
3.5. Yeah, it's interesting. It's not the same, is it? People don't
Mhm.
realize that. 3.5 hours includes the lecture, though, right, Nick? It's not like the lab was 3.5 hours.
The whole thing collectively was 3.5 hours, and obviously, like, I have to pause in between at a bunch of points to write stuff down and think
Yeah.
stuff through, so it ends up being way longer than 3.5
Yeah.
hours that I have to sit here and do that. So
Yeah.
I secretly, some people really want the asynchronous lectures and it works for them, especially because they can like fast forward through all my yapping. But at the end of the day, there's something to collectively being in the same, all right, we're not in the same spot, but we're all locked in here together. It helps to do it that way.
I like in-person learning, so this is the closest that we can get. So
Exactly. That's why I'm providing the service. I think it's important.
So-
All right. Last two problems are just on Kepler's laws. Wicked easy. We'll crash right through them. I don't know, Mariah, do you want to read a question? Are you done to read chapter 3, number 53?
Yes, let me just grab it. I have it up.
Wait, so when you guys watch the lectures, did you watch the ones from this semester or did you watch it from last semester?
this semester.
Okay.
All right.
Chapter 3, number 53.
Is it the new orb or the new planet orbit? Is that the correct one?
Yep.
Okay, great. A newly discovered planet orbits a distant star with the same mass as the sun at an average distance of 112 million kilometers. Its orbital eccentricity
Yep.
is 0.3. Find the planet's orbital period and its nearest and farthest orbital distance from the star.
Okay. The planet has an orbit with a distance of 112 million kilometers, an eccentricity of 0.3. Now, did they do part A and B, or did they just kind of ask all those questions in there?
It's kind of all of it in one.
Okay. We're trying to find the period of the planet, and then we have to find the closest and farthest approach, perihelion and aphelion. Actually, when it's another star, they call it periastron and aphastron, but I'm not gonna mince words there. Okay, let me walk you through this. To find the period, we're going to use the formula p squared equals a cubed. A is the distance, okay? But A has to be the distance in astronomical units. Our distance was not given in the right units. It was given as 112 million kilometers. Tegan, are you still with me? Who's floating around out there? Hi, Tegan. You want to help me do some conversions? I thought that would be cool if you could help me with that.
Sure.
We can give it a try anyways, right?
Mm-hmm.
Okay. So Tegan, do you have the 4 steps of dimensional analysis in your notebook? Can you check?
Yeah, I know how it works.
Or if you know how it works, then you can just tell me what to do. But I was trying to give you some guidance there if you needed it.
I know there's it's number times something over another number.
Right. Let's follow the steps. Get those steps out for me. Trust me. It'll be good that way.
Yikes.
Should be like in the first day, it'll say 4 steps of dimensional analysis with some stars next to it.
Oh, I don't think I have those notes. I think those are the only ones that I missed.
Nuts. Okay, does anyone else have them and we can read it out to Tegan?
Yeah, I have them.
All right, what's step 1?
Write down number to convert to its units.
All right, so Tegan, you're going to eventually have to get those in your notebook. This is really important. Step 1 is write down the number to convert with units. What should I write down?
Is it 0.3?
Nope, that's the eccentricity. We're
Oh,
12.
112 times 10 to the 6 kilometers.
Good. Okay, what's step 2 of dimensional analysis? Whoever had that. Right?
Oh, yeah. Sorry, I forgot. Multiply by a division bar.
All right, that's pretty straightforward.
And then
Step 3.
Step 3, units to guide, units put first to cancel.
Whoa. Put the units in first to cancel. Uh-oh, dog attack. Put the units. Is that yours, Tegan? You got a dog going crazy back there?
Yes, we do.
You're off the hook. Mariah, why don't you walk us through? Tegan's got a dog fight in progress here. No wonder people are having a hard time learning from home. All right, okay. Mariah, let's put some units in here.
I'm actually gonna have to.
Yeah, Tegan. All right, I'm muting you, Tegan. Tegan, you better get some headphones, okay? Mariah, can you help me put the units in top and bottom there?
Yeah. So we're changing it to, you said, is it arc seconds or?
No. The distance needs to be in astronomical units.
Okay. So I'm trying to remember what's like the.
No. You're getting ahead of yourself, Mariah. I just want you to put some units in top and bottom. You don't need to know any numbers yet.
Okay. So would the top one be AU? I forgot what
the
thing. Okay. So AU on top, and then the bottom is kilometers.
Good, because that way they cancel out. So that's step 3. The reason why okay, Tegan, sorry about that. Good. Don't get bit or anything. Okay, so I'm worried about that dog fight there. Remember, step 3 is, that's okay. Tegan, just please finish these problems later. Sorry it took so long, everyone. The kilometers cancel. Now we have to find the conversion factor, right? Who knows the conversion factor?
I think I just found it.
Okay, read it to me.
Is it 1 AU equals 150 times 10 to the 6th?
Good. So which number goes where?
So 1 AU goes on the top. Oh God, my dog's now. Then 150 times 10 to the 6th is at the bottom.
Good. Okay, guys, so take your calculators, use the EXP key, do 112 EXP6, divide by 150 EXP6. Oh man, I'm feeling the burn here, and I ain't talking Bernie Sanders. I'm talking whatever I did to myself last night is catching up with me. Anyone got a number? Yes, thank you, Zach. 0.75 AU. Always put the 0 out front, Zach. It's good style. People are notoriously lazy about decimal points. Okay, now we're going to be able to plug this into p squared equals a cubed. So I like to take the square root of both sides. I'm going to write p is equal to the square root of a cubed. P is then equal to the square root of 0.75 cubed. And now I'm going to show y'all how to do that on your calculators.
Wait, I can't see the rest.
Sorry.
Now I got it.
Testing. Testing. Test.
Is- I can hear you.
Can you hear me now?
Yes.
Okay.
Yeah, you're
Whenever I open up, sometimes when I open up Logitech, it screws up my mic. All right, Andy, you got that?
Yeah, I got it. I got it.
I'm going to show you the buttons that we're going to use for this problem, okay? Let me autofocus close to the screen. Let me get a pencil. Okay. In the upper boxes here, the keys that we're going to want is, there's the square key. Above it in orange is the square root key. And I want you to notice over here, that's your x cube key, and this is your cube root key, okay? Now our job, the board is fuzzy, but we're gonna do 0.75 cubed, and then we're gonna square root it. So follow along with me now, okay? Clear it out. 0.75, shift x cubed, now we're going to square root it.
What is it? Shift?
Shift, and then this key is x cubed.
All right.
Now we're going to square root. So we're going to go shift, square root. Do you guys have that? I'm going to round it to 2 sig figs for fun, 0.65. And the units are always years when you calculate the period. So this is like your first time going through this, so it's a little weird. That's one of our answers. All right. We also have to get the perihelion and the aphelion distances. The formulas are really simple. The perihelion is A, the distance, the semi-major axis, times open parentheses 1 minus the eccentricity. The aphelion is A times 1 plus the eccentricity. I'm going to keep my A in astronomical units because that's a nice unit to use. So on the top, I'll have 0.75 AU times 1 minus 0.3. On the bottom, 0.75 AU times 1 plus 0.03. I'm going to show you guys how to punch that. Class, we're going to be using our parenthesis keys here and here. So let's do the top first, okay? Clear that out. 0.75 times open parentheses 1 minus 0.3. Then we close parentheses, and that does the parenthesis part. And then we hit equals. Let's round it to 2 sig figs, 0.53 astronomical units. Sorry, I'm smushing into the edge there. Do you guys want to try that one now? Do it the same way, but this time plus. Someone get me an answer for the aphelion.
0.98
Good. And the units?
astronomical units.
Good. So we'll box that. Box that. Whew. The next problem is exactly identical to this. So we're going to do it faster this time. Mariah, you just read us number 53, correct?
Yes.
In the interest of time, I'm going to ask you to read 54 too, but hold on. Let me let Nick and Andrew and everyone catch up there. Andrew,
I
let me
got
know
it.
when you're done.
I'm all set.
Okay. And Andy?
Yeah, I'm all good.
All right, I'm erasing. All right, chapter 354.
Yep. I saw you pronounce it, or I heard you pronounce it earlier. It's not Haley. Or is
Haley's Comet? Yeah, Halley's Comet. I don't know.
okay. Okay, I heard it differently, so I was like, oh my god, I've been saying it wrong this whole time.
Honestly, sometimes I say it back, and sometimes I say Halley's Comet, sometimes I say Haley's Comet. I don't know.
Okay. All right. So Halley orbit. Halley's comet orbits the sun every 76.0 years and has an orbital eccentricity. That's a word so hard to say.
Yeah, let me try with you. Eccentricity.
Eccentricity of 0.97. And then part A is find its average distance from the sun, semi-major axis.
Okay. This is a reverse of the problem we did before. Instead of p squared equals a cubed, we flip the equation around. A cubed is equal to p squared. Now, they've given us the period, p, so we're going to take the cube root of both sides. A is equal to the cubed root of p squared. Now, the period is it's not 0.76 years, it's 76 years, right? I was about to say we'd be able to see Halley's Comet every 6 months or so.
Yeah.
Sorry about that, guys. I'm a little squishy right now. So it's the cube root of 76 squared. I'm going to show you how to do that now. Once again, the square key is here, but we're going to want to use the cube root key, which is shift and then the plus minus key. So we'll type 76. Then we're going to square it. Just hit that key.
What's the key? X to the second.
X squared. Yep.
All right.
Then we're going to go shift, and this key is the cube root.
What's the cube root?
Shift and then plus minus.
So it's 76 x to the second shift, and then shift
and cube root. You guys should be seeing 17.9. I'm going to round that to 18 years. I'm sorry, not 18 years. This is a distance, 18 astronomical units. In part B, we're going to calculate the perihelion and the aphelion distances. The perihelion is A times 1 minus E, which is 18 AU times 1 minus 0.97. The aphelion is A times 1 plus E, 18 AU times 1 plus 0.97. Ugh. Okay, why don't you guys bash those out for me? Use the parenthesis keys. Zach's telling us 0.54 AU for the perihelion. And sorry, I gotta look at that chat again. He also says that he got 35 AU. Nice rounding, Zach. I like your moves. 35 AU for the aphelion. This means at its closest approach, Halley's Comet goes inside the orbit of Venus. At its greatest distance, it's almost as far as the orbit of Pluto. So this comet truly travels the entire length of the solar system on its journey around the sun. A very, very eccentric orbit. Halley's Comet it goes all the way in and all the way out of the solar system. Wow, guys, that was a whopper. I'm real sorry about that. I wish I could have gone faster, but I don't know how I could have. Not all the homeworks are going to be that nasty, so I apologize a bit. This is some heady stuff with the coordinates, okay? Next week, homework will be a lot. Actually, next week's kind of rough too. All right, it's going to be a little rough before it gets better. Okay, in any case, next week's lab is easy, so I'll see you guys on Tuesday. Bring some pencils and a string if you can. Bring thumbtacks and a string if you got it.
And cardboard.
And cardboard. You can just cut a cardboard wine box with a box cutter or something. Have pencil, calculator, and a ruler. Okay, guys, please submit that right away. Thanks for toughing it out with me.
Thank you.
Time for me to
No
take a
problem.
nap.
Thank you.
All right, I'll see you guys on
Bye.
Tuesday.
Bye.
Bye.